I think I might get another cup of coffee. Now that I have my coffee, I'm ready to watch radar. You need to hire a stand-in for these long streams. I mean, I could take a 30-minute break like what I used to do. There was that video about the SR-71 that I kind of want to put up. It's 26 minutes. Here. I'm going to go get another pot of coffee and then stretch. I will be back momentarily.
The National Aeronautics and Space Administration's Dryden Flight Research Center, Edwards Air Force Base, California. NASA's program for research into supersonic flight began at Muroc, California in the spring of 1947 with the X-1 rocket airplane. Hypersonic flight research began with the X-15. A great deal of information was obtained in the high-speed, high-altitude, and short-duration flight envelope with the X-series research vehicles. Sustained supersonic flight research continued with the XB-70. Having exploited the potential of these vehicles, NASA required a more advanced flight platform. To fulfill this requirement, a joint United States Air Force-NASA program was initiated using the YF-12. This program would extend NASA's capability into sustained high-altitude, high-speed flight. NASA's use of the YF-12 sought to achieve many objectives. Some of the priority programs include investigation of predictive techniques in new design for structural, stability and control, and propulsion systems. When NASA received the YF-12, significant testing had been completed, providing a ready research platform. The YF-12 is a member of the triple-sonic Blackbird family, a product of the Lockheed California Company facility known as the Kelly-Johnson Skunk Works. The YF-12 was conceived as a high-altitude, high-speed interceptor. Its basic mission, maximum range intercept with an operational radius of over 1,000 nautical miles. The basic design concept was a low aspect ratio double delta wing with the propulsion system located in the flow field where base drag would be minimized. Extensive use was made of existing NASA wind tunnel facilities. Beside the usual lift, drag, and stability testing at low and high speed, transonic measurements were particularly critical. The thermodynamic and aerodynamic loads on a Mach 3 airplane are staggering. The operational temperature range for the YF-12 airframe would be from a minus 65 degrees Fahrenheit to a plus 800 degrees. During cruise Mach, the leading edges and inlets run over 790 degrees Fahrenheit, wing and fuselage 450 to 500 degrees, afterburner and ejector between 900 and 1100 degrees, and the tailpipes are glowing white hot. This airplane, capable of sustaining speeds of over 2,000 miles per hour, overcame a giant hurdle in the engineering and manufacturing state-of-the-art. Lockheed had been working with titanium on a research basis since 1949. An advanced alloy of this metal was selected to achieve the strength-weight ratios required in this hostile environment. Full-scale mock-ups and test rigs were used extensively. A four-body section was constructed and subjected to the heat and stresses to be encountered. From these tests, much was learned about hydrogen embrittlement, heat treat procedures, and forming methods. Test panels of the wing box were built and subjected to loads which would be encountered during typical flight maneuvers. Also, it was necessary to provide a means for the skin to expand with an increase in temperature and Mach number. This was accomplished by using cord-wise corrugation and special methods to attach the wing surface to the spars. A hot forging process is used to bend and shape titanium billets into structural segments of the airframe. Extremely high pressure and controlled environment are required to form the complex shapes. The practical machining of titanium required the development of cutting machinery, drills, power heads, profilers, and lubricants. The manufacturing of close-tolerance titanium sheet metal parts required a completely new process referred to as hot sizing. The hot press applies pressure to the parts, holding them at a constant temperature and pressure for the processing period. A comprehensive series of static and proof tests were conducted to substantiate structural integrity. 93% of the structural weight of the YF-12 is titanium. Functional mock-ups were used to prove systems before installation. The complete fuel system was subjected to elevated temperatures in climb, dive, and all aircraft flight conditions. Components of the pumping, refueling, purging, feed, vent, and dumping systems were operated at temperatures above 500 degrees Fahrenheit and at altitudes above 80,000 feet. Landing gear components were tested to destruction. Standard aircraft tires would not stand up to the elevated temperatures. A radical design was required to endure the long heat soak of Mach 3+ flight. Landing gear tests were run on the drop tower. There were no hydraulic fluids, pumps, or seals that would operate continuously at 600 degrees Fahrenheit. The automatic flight control system, servos, actuators, and cables were installed in an oven and tested for hundreds of hours. Conventional control cables did not pass the test. A watch spring material known as Elgiloy was used to meet the life cycle requirements. The automatic flight control system includes, in addition to the mechanical and hydraulic components, a stability augmentation system, autopilot system, and Mach trim system. This provides stable flight throughout the wide range of operation. Safety of the flight crew was the prime consideration in the design of the escape system. It was essential to provide safe egress throughout the complete flight spectrum from takeoff to cruise. High-temperature electrical and electronic components were practically non-existent. Wires, terminals, connectors, and transducers developed for the space age were capable for short-duration temperature bursts, but not sustained high-temperature flight. The cockpit, missile bays, and components required a cooling and pressurization system far beyond the capability of existing design. This brought about an innovation, utilizing inlet bleed air and using the aircraft fuel as a heat sink. Inlet bleed air is in the range of 800 to 900 degrees Fahrenheit. Cooling with this air required a unique approach in the design of air turbines and heat exchangers. The air inlet system involves positioning the spike and matching various bypass airflows. The purpose is to maintain the optimum shock position on the cowl to maximize thrust and minimize drag. In the event of an aerodynamic disturbance in the inlet, known as an unstart, rapid sensing of the various parameters is necessary to regain control of the airflow. The disparity in thrust during an unstart is compensated for by the stability augmentation system. This provides aircraft control compensation in a fraction of a second. It is extremely difficult for the pilot to manually correct for such disturbances. The YF-12 fuselage is equipped with compartments in the chine area to accommodate the missiles. Missile loading and static drop tests were conducted. The fire control radar was tested for target search and acquisition above and below and at long distances, beyond the launch platform. Live missiles were launched against a variety of drone aircraft targets. Target interception and destruction was demonstrated. On May 1st, 1965, the YF-12 demonstrated its excellence by capturing 9 speed and altitude records in one day. Kelly Johnson, Lockheed's senior vice president and chief engineer on the YF-12, has often said, "Everything on the Blackbird, from rivets and fluids up through materials and power plants, had to be invented from scratch." The NASA Flight Research Center received the YF-12 in 1969. The initial program objective was to compile instrumented flight data against which various predictive design tools could be compared in order to assess the state-of-the-art of those predictive design techniques. These tests would contrast early transonic V-47 high aspect ratio wing research data with the low aspect ratio wing data of the YF-12. It also offered an opportunity to compare loads and structures data from the rapidly accelerating X-15 research airplane with the long heat-soaked cruise of the YF. NASA and U.S. Air Force Flight Test Center personnel prepared the Blackbird for its new role. Thermocouples and strain gauge bridges, along with other airplane instrumentation, was installed. Point loads were applied to the airplane under ambient temperature conditions to calibrate the gauges. A flight test matrix was selected, flying varying configurations of weight and center of gravity at cruise speeds up to 3 times the speed of sound and at altitudes up to 80,000 feet. Temperatures were recorded for each configuration throughout the entire flight. In addition to loads and temperatures, structural deformations were measured at all test points. In order to precisely calibrate the thermal effects on the strain gauges, ground heating tests were conducted. A stainless steel oven conforming to the contours of the airplane was built. Heat lamps were wired inside the oven. The entire airplane was placed in the test fixture and heated to flight-measured temperatures to calibrate thermal effects on the strain gauges. The tests were controlled by a digital computer program using in-flight temperature time histories. Ground vibration tests were conducted to aid in defining the structural mode shapes. The calibration of the experimental instrumentation and the flight tests formed the nucleus of the empirical work, thus paving the way to assess the state-of-the-art of the predictive techniques. The theoretical work was built around 2 large computer programs known as Nastran and FlexStab. NASTRAN is a finite element program that predicts structural behavior. This program was developed as part of the NASA space program, and the YF-12 exercised its application to aircraft to the fullest. Utilizing nearly 8,000 degrees of freedom, it took several hours to compute the behavior at each desired condition. FlexStab modeled the YF-12 with some 350 equivalent panels and was used to predict the external aerodynamic loading on the airplane. FlexStab predictions were augmented with pressure distributions measured on a 1/12th scale model of the airplane. This structures research has been completed and reported to the industry at a classified symposium in June of 1974. This work provides an accurate design model for future aerospace vehicles. The current program, directed by the NASA Langley Research Center, will concentrate on the development of new lightweight structural materials and fabrication techniques. 2 new types of titanium panels have been fabricated, tested, and are acquiring service life history. One uses a weld-brazed process, and the other is of titanium honeycomb construction. A series of composite panels is under consideration. A boron aluminum honeycomb panel will soon be tested. One major objective of the panel program is the determination of realistic cost information for the fabrication techniques. One of the most important facets of NASA research is the performance propulsion program. The theory in these disciplines is not as highly developed as in the structures area. Therefore, greater reliance is placed on wind tunnel testing. The inlet on the YF-12 is a vital element in providing efficient high Mach cruise performance. Air is compressed to 40 times ambient pressure as it slows from free stream velocities in excess of Mach 3.0 to Mach 0.3 at the engine face. A translating center body controls the shock waves for efficient deceleration of the inlet air. Bypass doors precisely match the inlet air to the engine face. Dynamic variations in airflow occur rapidly. Therefore, improper matching of airflow, even momentarily, builds pressure in the inlet and suddenly expels the shock waves, increasing drag drastically. This situation is referred to as an unstart. During an unstart, the airplane gyrates violently due to the aerodynamic disturbance surrounding the inlet. Full-scale inlet tests were performed in the NASA Lewis Research Center 10 by 10 tunnel. A 1/3 scale inlet model was fabricated and installed in the NASA Ames Research Center unitary wind tunnels. The model duplicated the full-scale inlet, but the tests stressed dynamic measurements. It was tested to speeds in excess of Mach 3. 3 YF-12 Pratt & Whitney J58 engines were operated in the high-altitude Lewis Research Center Propulsion Simulation Laboratory. Tests were run to calibrate engine airflow under varying simulated flight conditions. Engine products of combustion were also surveyed. The analysis of dynamic data is a relatively new art. The dynamic data analysis computing setup prepared by North American Rockwell for the B-1 airplane is being used to process the YF-12 dynamic inlet data. Ground-based as well as airborne photographs of the YF-12 exhaust wake have disclosed that long-term wake dissipation characteristics are not predictable with present theory. In addition, U-2 aircraft from the NASA Ames Research Center have probed the YF-12 near-term exhaust wake to make comparisons with the products of combustion as measured by Lewis Research Center. Follow-on work is being considered for the YF-12 inlet research program. Fast-acting pneumatic poppet valves are being placed around the periphery of the full-scale inlet at the Lewis Research Center. Small-scale wind tunnel tests indicate that such a mechanization can reduce the occurrence of unstarts and permit more efficient inlet operation. It remains to be seen if the small-scale results can be duplicated in flight. Other wind tunnel tests have helped to establish the feasibility of testing a modern inlet by placing it on the back of the YF-12 between the vertical tails. This installation can be put into place and removed quickly and easily and permit the evaluation of a wide range of inlet geometries in a cost-effective fashion. Experience on the B-70, the YF-12, and more recently on the Concorde shows that as speed and altitude increase, the ability to hold altitude precisely becomes more difficult. Several factors influence this deterioration in ability to control altitude. At high Mach number, the large energy vector dictates that if airplane attitude changes, even slightly, vertical velocity will change, and so must altitude. But perhaps more importantly, the outside air temperature at high altitude can change abruptly because so much distance is covered in such a short time. These excursions far exceed any values that could be tolerated in air traffic control. The examination of data from many flights showed that the inlet bypass air was the most significant factor in the thrust change produced by the temperature variations. Tests were run on a 1/12th scale model of the airplane at the NASA Ames Research Center to examine the problem in a more systematic manner. Using the 1/12th scale data as well as flight data, an extensive simulation of the airplane and its propulsion system was mechanized at the Lockheed Bry Canyon facility. An autopilot mechanization of altitude hold was synthesized to reduce altitude excursions by an order of magnitude in flight.
What was that? Was that a computer?
Further mechanization
What the frick?
hopes to make more optimum blending of airframe and propulsion system controls. The YF-12 is carrying a series of aerodynamic experiments into the high-speed regime as a sort of flying wind tunnel. One, called the aft facing step, measures the base drag behind an inclined ramp. Data from this experiment will give insight into the effects of manufacturing tolerances of lap joints, probes, or other protuberances under boundary layer and Reynolds number conditions unobtainable in existing wind tunnels.
Yeah, okay. I understand some of these words.
Skin friction and boundary layer growth have been measured on the long, straight underside of the YF-12.
Oh, cool.
Since skin friction drag can account for as much as 1/3 of total drag at Mach 3, it is important to be able to predict it accurately.
Did you guys hear that? Skin friction accounts for 1/3 your total drag at Mach 3, meaning that the air just passing by the side of the vehicle causes crazy amounts of drag at that high of speed. It's called skin drag. Yeah, that's nuts. Can I get a link for the video? Yeah, sure, man. This is actually off of Wikipedia. It's off the YF-12 wiki. Which is why it gets so hot in the cockpit and why the plane expands. Can you believe that? Yeah, that the drag is literally coming from air hitting, like colliding into the side of the airplane. And that the compression of gases creates heat, which is nuts. I mean, don't get me wrong, any airplane flying through the atmosphere is going to have air molecules bouncing off of it. But at Mach 3, that collision is a little more violent, let's say.
This is an extension of work begun on the B-70. As with the aft facing
Yeah, exactly,
step,
Aqualex,
the boundary
right?
layer measurements made in flight cannot be reproduced in any existing.
I actually realized that this is while I was taking a break from the cast yesterday. I realized that the entire YF-12 program was a front to make everyone think that if they saw one of these, it was probably a YF-12 and not an A-12 or an SR-71. Yeah, the whole thing was just kind of like, oh yeah, we're working on an interceptor. No, it's not a reconnaissance plane. It's an interceptor.
Wind tunnels. Pressure surveys are also being made on the rear fuselage to get a better understanding of fuselage boat-tail drag effects in a real flight environment.
Energetic.
This is
Yeah,
another
there you go,
area where
Elmore.
difficulties have been experienced with accurate wind tunnel drag measurements, especially at transonic speeds.
Interesting.
A series of cruciform delta wings have been added to the nose boom.
Oh, very nice.
Differential pressure measured from opposite wings allow for the resolution of gust velocity measurements as small as 1 foot per second.
I don't think Neil Armstrong flew
When the total
in an
velocity
A-12.
approaches
He was
3,000
X-15.
feet per second.
I don't know if he flew one of these things.
Gusts and turbulence have been experienced at even the highest altitudes flown on the YF-12.
Oh, hey, audiophile. What's up, dude?
These atmospheric phenomena
Never
exert
told me
measurable,
that.
unfavorable
cool.
effects on the dynamic inlet behavior and on the flight crews. Flight crews
Chest
are
hair.
wired for sound on every flight.
Yeah, it's been a bit, man. How you
Measurement
been?
of heart parameters as well as
good to see
exhaled
ya.
gases give a continuous evaluation of the effect of high-speed flight on the human.
On the human.
Long
Not
periods
this
of
guy,
flight in
but on the
pressure
human.
suit cause dehydration and fatigue. It has a treacherous, gradual, and cumulative effect on pilot performance. Efforts are also being made to correlate the relationship between biological measurements and crew workload in order to quantify crew workload.
Look at the step gantry to get into this thing. See how wide that staircase is? It's because you have to have a spacesuit to get in this thing. You're not just wearing a flight suit, right? You have to have the whole damn spacesuit.
The most spectacular aerodynamic experiment, at least in looks, is the hollow cylinder cold wall experiment. The idealized aerodynamic shape of a cylinder, 10 feet long and 18 inches in diameter,
There you go, audiophile. Right
is
on, man.
cantilevered 4 feet below the underside of the fuselage.
Look
The
at that
cylinder
plane,
is immersed
man.
in nitrogen to cool it to minus 100 degrees Fahrenheit. It is covered with an insulating blanket, flown to Mach 3, and the blanket is pyrotechnically removed, exposing it to a temperature of 500 degrees.
Interesting. Dude,
Instrument
look at that.
built into the cylinder will make a variety of measurements such as heat transfer coefficient, boundary layer transition,
Yeah.
and aerodynamic noise, all free of the constraint to wind tunnel wall interference effects. By testing the same cylinder in the wind tunnel, the tunnel interference effects can be better understood and calibrated.
Nice F-104.
This is the YF-12, a national asset, a vehicle providing advanced research today for tomorrow's industry, a flying wind tunnel, furnishing NASA with the technical data to keep America the world leader in aerospace.
Cool. Hey, Alleviate. 43 months. Thanks, buddy. The Lockheed California Company. That's cool. All right. Okay, we're back into Star Raker. Yeah, that's really cool. That's really cool. They didn't quite know how far away tomorrow was going to be. Yeah. Dude, when I first looked at like YF-12s and saw that they have the cut strake right there, I thought that looked stupid, but I don't know what it is. The more I look at it, the more I kind of like it. Just read the instructions, is now departing for Starlink. Nice. Audio file, yeah, your dad worked on the instrumentation of the SR-71s during Vietnam, as well as having his flight rating. After he got a Purple Heart in the Army, he IST'd into the U.S., inter-service transferred into the USAF, and that was his assignment. Cool, man. That video seemed like an internal, for official use only video. Something in the public archive, but yeah. Did you guys see the intake? The intake is on a gigantic screw jack, like a corkscrew, just pulls it back and forth. It's really wild stuff. The cone intake is the reason why this whole thing works correctly. What this thing is designed to do is basically split the air and make a wake, and the nose cone on the intake actually retracts into the intake duct. And the reason why it does that is to channel the wake, the boundary layer, into the engine. And then from there, the boundary layer bounces off the outer wall and bounces off the inside of the intake and the outer wall and the inside. Like it bounces around in there, and that's what makes the ramjet work. They feed the ramjet subsonic air at high compression, and it just shoots out the back. No moving parts. Spray fuel into it, and you're good to go. Because the cameras were heavy, without the cameras in the forebody, they needed to reduce the forward lift at supersonic speeds. Yeah, I think it looks cool. I think it looks cool. Like, I especially like looking at the YF-12 from the side. Like, that's a looker of a plane. Look at that thing. Woo! Like that, the straight conic nose looks very choice. That's a looker. Woof! I like that. That's really cool. Random one. Saw Oppenheimer for the 4th time alleviate? Damn, dude. What a brutal shape. Yeah, Toto, it's pretty cool. Can you imagine if the engine had been designed to do ramjet stuff from the start? I'm still coming to terms, yeah, Tessa, I'm still coming to terms with the fact that the J58 was designed by mistake. Like, I know good and well that that's not the exact way to put it, right? But the whole ramjet thing, being accidental is still kind of like, what? What's the difference between a ramjet and a scramjet? Airspeed. Ramjets need air going subsonic to work correctly. Scramjets can take supersonic air and combust it. Scramjets are nuts, dude. The crazy thing about a scramjet is it basically just looks like a funnel. It looks like an hourglass. That's about it. Nobody funds silly-looking planes. You're not wrong. Yeah. Chat was telling me about that the other day, and I'm like, wait, they did this by accident? Okay. Yeah, see? Look. It takes... The boundary layer goes... They end up channeling it into the engine. Can you believe that? Center body bleed, forward bypass doors closed, will open as required to position the inlet shock. That's nuts, dude. What the heck? At the same time this was flying DC-6s, we're still flying passengers in commercial service. Dude, I don't know. That's impressive. That's impressive, dude. This, guys, I'll be honest, this is still hardcore, even by today's standards. That is really, really insane technology. Like, even by today's standards, turbo ramjets are still pretty damn impressive. All supersonic jet engines slow down the intake air to subsonic. Yeah, that's right, Maggie. Yeah, it turns out that if the air going in is going faster than the air coming out, the jet engine does not like this. Yeah, right? You don't like that. How did they come up with this accidentally? I forgot the engine. Did they forget the engine covers before flight? No, I think, Adam, I haven't read enough about it, but I'm pretty sure, like, I've kind of blazed the cliff notes. They were basically trying to slow down the air to go into the J-58 to go faster, and they ended up making a ramjet by accident. That was the idea. They were trying to... What were they trying to do, guys? They were trying to lower the pressure in the intake, I think. They were trying to lower the pressure in the intake going into the engine to try and feed the intake subsonic air. But then they realized later that... what was it? You could just take that subsonic air and burn it, and then you could shut the jet engine off. Yeah, Hermes made an operational ramjet, yeah. Do you think we will see a decrease in development of new airplanes now that drones can be mass-produced and are cheaper? No. Muskrat, I don't think a new technology ever entirely replaces an old technology. Case in point would be jet engines, jet-powered airplanes versus propeller-driven airplanes. There are certain things that a person inside a plane can do that a drone can't do, and vice versa, in any particular situation. I think it'll be like a supplementary thing. Like computer, think like if you've ever played StarCraft, think Protoss carrier. Computer-controlled mothership with launching a bunch of drones, and the drones are controlled from said computer, said mothership. That's what I'm talking about. You know what I'm saying? Good question, though. They were trying to bypass the engine to reduce intake pressure to alleviate drag. Yeah, Mage, exactly. Slow down the air, but at the same time increase efficiency by increasing the bypass ratio. Then, ooh, wait, we could totally just use the bypass. Like, the fact that they figured that out by accident is still kind of nuts to me. Modern planes are basically drones with human flight computers, considering how advanced autopilot is now. Yeah, of course. Check out this video. I know about Hermes. Yep. Oh, if you haven't seen this... Oh, okay. That's a different video. I thought you were... I just got to be careful about showing other people's YouTube videos. But, yeah, we'll yeah, it plays ping pong or pinball inside of the intake. It's really wild stuff. This is by Tech Laboratories 9 years ago. Yeah, let's just get to the good part. Boop. Yeah, wait a minute. Is that... How... Really? Really? Curious. Yeah. Zarby, even if it was okay, I still don't like doing that. The final wave is because of the expansion of the internal chamber right before it. Yeah, Mage, I noticed that. That's why I never noticed that spike in the... See this right here? That little kinky thingamadoo right there. Dude.
shockwave before moving into the
let's
multi-stage,
back it up a
the
little
Pratt &
bit.
Whitney J58 engine, the convergent-divergent ejector, and the airplane body.
Right, Zarby?
At speeds below Mach 2, the J58 acts like any other afterburning turbojet engine. Air flows into the nacelle through the inlet, where it's allowed to diffuse behind the supersonic shockwave before moving into the multi-stage axial compression.
Dude, I know that this is kind of garden variety stuff, but the fact that they use the boundary layer to lower the pressure is that's pretty trick. That's a pretty trick solution right there. Once again, I know most intakes do something like this. I understand that. I'm saying that is pretty cool. That's not anything new, but yeah.
Compressor, which looks like this, but bigger. Here the air is compressed before heading into the burner where fuel is added for combustion. The heated exhaust turns the turbine and provides the engine's forward thrust as it's accelerated to high speeds by the ejector. The turbine turns the compressor and keeps the engine cycle going.
Yeah.
Just after the turbine is the afterburner, where more fuel is added to the exhaust in order to get as much of the oxygen out of the air as possible. While afterburners allow for powerful bursts of acceleration, they're really inefficient, costing huge amounts of fuel for the increased force. What makes the J58 engine so different than all other turbojets are these 6 bypass tubes, which you don't find on these diagrams. The tubes open when the plane is flying at speeds greater than Mach 2.2, moving compressed air from the 4th stage of the compressor directly into the afterburner. This allows the engine to act more like a ramjet, which allows the SR-71's afterburner to operate at a much higher fuel efficiency. The forward motion of the aircraft handling most of the air compression at a ratio of about 39:1, with the 4 turbine stages.
You showed me this the other day. I remember now.
Is adding an additional compression of about 1.6:1. The combined action of the turbine and ramjet compression makes the J58 a very unique type of engine, a turbo ramjet, and allows the plane to cruise at speeds that would make a normal turbojet melt. Than all other turbojets are these 6 bypass tubes, which you don't find on these diagrams. The tubes open when the plane is flying at speeds greater than Mach 2.2, moving compressed air from the 4th stage of the compressor directly into the afterburner. This allows the engine to act more like a ramjet, which allows the SR-71's afterburner to operate at a much higher fuel efficiency. The forward motion of the aircraft handling most of the air compression at a ratio of about 39:1, with the 4 turbine stages adding an additional compression of about 1.6:1. The combined action of the turbine and ramjet compression makes the J58 a very unique type of
Turbojet, active compression through turbine-driven axial compressor, ramjet, passive compression through inlet geometry and aircraft motion,
engine, a turbo ramjet, and allows the plane to cruise at speeds that would make a normal turbojet melt.
Okay, I have a bonehead question. Why go through 2 stages? Or why go through the initial 2 stages? Why not just a complete bypass into the afterburner? Maybe he'll answer.
The Blackbird's inlet design is as important to allowing the J58 to do its thing as the engine itself, so let's see how it works. In the middle of the inlet is this symmetrical spike, called the inlet spike or center body, and behind it is the diffuser, where...
I know about this part. Not so much that part over there. This is the part that matters. Because they were using it to reduce heating on the compressors. That's why the ramjet aspect was accidental. So they were using the J58 compressor bypass to keep the compression heating down and ended up making something way more freaking powerful. It's a variable intake transistor. Watch, here, just watch.
Compressed air spreads out before entering the engine. At supersonic speeds, the inlet spike takes the pressure of the leading supersonic shock wave off of the engine so that the engine gets the best airflow. Inside the inlet, a second shockwave is formed called the normal, where the air coming into the nacelle transitions from low-pressure supersonic speeds to high-pressure subsonic speeds.
A lot of intakes do basically that. The quick and easy way to figure this out is that the jet engine, the air coming out of the back of the jet engine can't be going faster than the air coming in the front. All right, that's one of the super simple explanations. It gets different than that. It's a little more complicated than that, but you don't basically want to get blow by in the jet engine. If the air is coming in too fast, it'll basically blow the combustor out. I mean, amongst other things, like that, it's once again more complicated than that. I understand it's more complicated than that. This is a complicated thing. I'm trying to keep it simple.
Where the normal ends up inside the inlet depends on the speed at which the aircraft is moving and the shape of the inlet and inlet spike.
Like I said, pinball machine.
When the aircraft hits Mach 1.6, the normal ends up in the best place inside the inlet for pressure recovery, which is the percentage of the pressure caused by the plane's supersonic flight forward that gets translated into usable pressure inside the diffuser for the engine. This ratio is a very high 90% for the SR-71 when flying at Mach 3.2. So to keep the normal in the optimal position for pressure recovery, the spike retracts 1.6 inches for each 0.1 increase in Mach number above Mach 1.6. This changes the relative geometry of the inlet, keeping the normal at the optimal position. When the plane reaches its cruising speed of Mach 3.2, the external shockwave is positioned directly at the inlet's lip, called the cowl, and the inlet spike is retracted 26 inches. It's at this speed that the J-58 turbo ramjet has its maximum fuel efficiency, with the pressure recovery at the inlet doing most of the air compression work for the afterburner. Okay, now that we've seen how the inlet, engine, and ejector all work together, let's look at the other details found inside the engine nacelle. Positioned inside the cowl is a cowl bleed that captures some of the incoming air and passes it through a ring of circular openings called shock traps that drop the airspeed to subsonic and guide it through the nacelle body around the engine for cooling. The air is drawn out of the nacelle by the fast-moving exhaust flowing through the ejector. At speeds below Mach 0.5, not enough air is coming through the inlet for cooling, so more air comes in through suction doors that are positioned midway along the nacelle. These close at Mach 0.5, which the plane only hits just after takeoff and just before landing. Before the ejector are a set of tertiary doors that also open at low speeds to prevent the ejector from creating places of drag caused by not enough air and exhaust flowing through it. These close at Mach 1.2 and stay closed for most of the Blackbird's flight, opening only for takeoff, landing, and refueling. Both the suction doors and the tertiary doors allowed the powerful J-58 to operate at speeds much slower than its high cruise speed. The engines are so big that each needs 2 muscle car motors on the ground to start it and rev it up to a self-supporting speed. But I digress. The last 3 details found in the nacelle are required for keeping the normal shockwave in place in the inlet. The first is the center body bleed, which connects the grill on the outside of the nacelle to a set of slits on the spike through a hollow center body middle. At low speeds, the center body bleed allows the engine to pull additional air into the inlet, while at higher speeds, the bleed wicks away the boundary layer, a layer of low-pressure turbulent air that normally sticks to the spike and reduces pressure recovery.
Who the frick? What? Wait a minute.
First is the center body bleed, which connects the grill on the outside of the nacelle to a set of slits on the spike through a hollow center body middle. At low speeds, the center body bleed allows the engine to pull additional air into the inlet, while at higher speeds, the bleed wicks away the boundary layer, a layer of low-pressure turbulent air that normally sticks to the spike and reduces pressure.
Oh, kiss my ass! Who the heck thought of this? What the heck? That's nuts, dude. How... bleeding away the boundary layer? Like, what, dude, who the hell even... What do you... Like, okay, all right. The reason why I'm freaking out is, like, that's hardcore. This is pretty hardcore aerodynamics, even by today's standards. They were thinking about this in 1957. Yeah, 1957. All right. Like, that... What? No. How? What are you... Like... How?
The first is the center body bleed, which connects the grill on the outside of the nacelle to a set of slits on the spike through a hollow center body middle. At low speeds, the center body bleed allows the engine to pull additional air into the inlet, while at higher speeds, the bleed wicks away the boundary layer, a layer of low-pressure turbulent air that normally sticks to the spike and reduces pressure recovery. Inside the inlet is a series of slots that run between the shock tubes that lead directly out of the plane. These are the forward bypass doors, which allow an analog computer to lower the pressure inside the diffuser by sending some of it outside the aircraft. But if the pilot wants to reduce drag during acceleration or provide additional cooling to the engine, he or she can open the aft bypass doors, which route the additional pressure through the nacelle and out the ejector. And that's it. That's how the J58 turbo ramjet inside of the Blackbird engine nacelle works.
Can I go through that last part one more time, please? I need to...
Details found in the nacelle are required for keeping the normal shockwave in place in the inlet. The first is the center body bleed, which connects the grill on the outside of the nacelle to a set of slits on the spike through a hollow center body middle. At low speeds, the center body bleed allows the engine to pull additional air into the inlet, while at higher speeds, the bleed wicks away the boundary layer, a layer of low-pressure turbulent air that normally sticks to the spike and reduces pressure recovery.
Huh.
Inside the inlet is a series of slots that run between the shock tubes that lead directly out of the plane. These are the forward bypass doors, which allow an analog computer to lower the pressure inside the diffuser by sending some of it outside the aircraft. But if the pilot wants to reduce drag during acceleration or provide additional cooling to the engine, he or she can open the aft bypass doors, which route the additional pressure through the nacelle and out the ejector. The outside of the nacelle to a set of slits on the spike through a hollow center body middle. At low speeds, the center body bleed allows the engine to pull additional air into the inlet, while at higher speeds, the bleed wicks away the boundary layer, a layer of low-pressure turbulent air that normally sticks to the spike and reduces pressure recovery. Inside the inlet is a series of slots that run between the shock tubes that lead to
one more time. I understand wicking away the boundary layer. I just want to hear what he says
slits on the spike through a hollow center body middle. At low speeds, the center body bleed allows the engine to pull additional air into the inlet, while at higher speeds, the bleed wicks away the boundary layer, a layer of low-pressure turbulent air that normally sticks to the spike and reduces pressure recovery.
Huh. They pull anything that's making drag out of the intakes. That's okay. Like, the Starraker engine start hardcore regen cooling to overcome that. I have something for you. Please watch this to the end. Trust me. A scramjet visualization. I mean, scramjets, yeah. I hate Facebook. Like I said, scramjets basically look like two funnels back to back. Nice. Who's running a scramjet at Mach 12? Ken York is. Cool. The concept here is to use beam power so you don't have to support combustion. They're zapping it with a microwave to create heat. Are they getting they're getting it to auto combust? No, just beaming a laser at it from the ground, delivering the heat that way instead of via fuel. Nothing is combusting, it's just heat expansion. Oh, okay. A maser, not laser. Okay. The fact that that's using beamed power, think about it. The solar beamed direct from orbit onto the engines. No combustion, just heat expansion providing thrust. That'd have to be one heck of a tracking system. Those microwaves would need to be pretty directly focused, but yeah, interesting. Question, why do you think we've never seen ramjets, etc. make their way into commercial planes nowadays? Alleviate, we pretty much right after Concorde got up and running, we figured out that sonic booms are, basically the fact that the sonic booms are so loud, it kind of killed flying planes that go supersonic over populated areas. Basically relegating Concorde to flying over the ocean, and that's about it. New York to London, New York to Paris. That's it. Which kind of sucks. It kind of killed the whole supersonic transport because... You know what the funny thing is, dude? Boeing made the 747 as a stopgap, anticipating supersonic transport being the norm. Yeah. The 747 was only designed to be basically something that they're going to use until supersonic transport, like in anticipation of SSTs, which is crazy, right? Can the heat transfer with the air going that fast? I don't know. This is at the upper echelons of what I understand for aerodynamics, fellas. Fuel consumption is way too expensive for commercial use. It was an intermediate design mutter. That's what Joe Sutter designed it to be. Yeah, anticipating supersonics. Yep. So if that new platypus build plane, the X-59, proves to help dampen sonic booms, maybe we could see that kind of shape tech on commercial airliners in the future. That's the hope, Wolfie. Yeah, the hope is that they learn something about damping out a sonic boom and damping out the shock waves that happen from with that make the sonic boom for the most part. Flags plus tweak scale equals yes. Ha 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 ha. Nice. I like that. I like that, Core. That's good. Neat. I already did my layout, so I think I'm good. But yeah, that is pretty cool. Time isn't the limiting factor on flights nowadays outside of ocean transit. Optimizing the climb is a bigger deal for the vast majority of commercial flight. Yep. So how quiet are they betting these sonic booms being? Basically, if you kind of thump a wall like that, it should just be a low audible thumping noise instead of a howitzer going off, which is pretty good. You're focusing too much about the speed of travel. That will always be a niche. The industry will go towards efficiency. No. If that's what you got out of it, Adam. No, I know. It's efficiency nowadays. It was efficiency until the fuel crisis. Yeah. Or it wasn't efficient. It was going faster until the fuel crisis. Yeah. We stopped building things to go higher, further, and faster basically around the 70s. And we started building for efficiency after that. Which is okay. Not very fun. It's just realistic. Yeah, no, you're right. I agree with you. Yeah, no, it's just, yeah. I didn't, yeah. So I gave the vibe that I wasn't. Yeah, no, that's not what I mean. Cool, I already hear plenty of thumps from your neighbors. Like someone out in the street shut a car door. Yeah, pretty much. Yeah, Hermias Bandit. Hermias is cool. Distant Thunder. Yeah, kind of like that. They are experimenting with Adelaide to London flights these days, and they have issues in route efficiency. Adelaide to London? I mean, if you want to spend 17 hours, 18 hours on an airplane. Yeah, 20-hour flight. Yeah, okay, 20. Like that's, I mean, that's a lot. Suborbitals could be efficient. You don't have to go through all the air. Maybe Elon's onto something with point-to-point, guys. I don't know, man. I can't help but think that like doing suborbital hops with something like this might be a good idea. But also, you know, you see this and then I also can't help but think that if you have something like an XB70 is super efficient, superbly efficient with compression lift. Like, you know, you could make the argument that you'll get there faster and way more efficient using the compression lifting. That shockwave, guys, right? The shockwave that the J58 intake gives off. See the shockwave, right? The wake that it gives off with an XB70 gets compressed underneath these wings. That's why the wings fold down at high speed. So the wings end up, because they're channeling that shock, the wake, the aerodynamic wake underneath the wings, it creates a ton of high pressure underneath the wings at high altitude while you're going fast. That enabled the XB70. I mean, they never really figured out what its flight ceiling was. Crazy. They never figured it out. They didn't get that far with the testing before the project got canceled. With the XB70 basically turns itself into a trimaran for air at extremely high speed. But get a bit of these numbers from the operational performance that they did fly. Fastest speed is 2,000 miles an hour. That's SR-71 quick with regular jet engines. Believe it or not, regular jet engines. Well, not regular jet engines. The intake on these is nuts, and they had 6 of them. The highest altitude was 74,000 feet at Mach 3. 74,000 feet with no turbo ramjet, at least to my knowledge. I'd have to go read more about the engine. What's the payload capacity? They never gave it a payload bay, Adam. Yeah, the project didn't get that far. They only built 2 of them. Yeah, and the second one crashed. There was a picture of it crashing right there. The only serial number 1. Look at the craft Hermes has planned. Yeah, see? There you go. Smart. I've seen that plane's about 15 minutes down the road. The XB70 was also light years ahead of its time. See those two? That guy, the YF-12, and the XB70, and the D-21 right there. well, 3 of the fastest things that's ever flown through the atmosphere, which is crazy. Other than space shuttle and space capsules and maybe some missiles too. Like in terms of people on board, these things are the fastest. The XB-70 was a freaking monster. Let's read about its engines, Tessa, real quick. I really have to get back to the Star Raker build, but oh hey Bree.
Hi.
What's up?
Nothing. How are you?
I'm good. Bree's here.
Bree is indeed here. Hey, did you make your phone call?
I did.
All
Went to
right.
voicemail.
You might want to try again, cause
Okay.
reasons. Oh, I was gonna ask Twitch Chat about her dishwasher.
I'll take care of it.
You said you didn't know what to do.
I'll figure it out. Why'd you say that out loud?
What? The dishwasher? Cause you told me you didn't know what to do.
I'll figure it, but I said I'd figure it out
No,
right after that.
I said, what are we gonna do? And you said, I don't know.
I'll figure it out, okay?
Alright.
Are you following the planned test flights for the X-59? Yeah, the X-59 is, hopefully it's a game changer, Stormcrow. Do you have a 9mm, just shoot the dishwasher? I don't think shooting the dishwasher is going to fix it, Clayton, but, I mean, maybe.
Yeah, if I can entertain chat if you want to go make your phone call.
I don't...
What up?
Never going to get the Star Raker done, man. I kind of...
Yes, your video game thing is never going to finish, even though you have all the time in the world to finish your video game thing. Go make your phone call.
I'll be right back.
Hi! Play KSP for us, please? KSP's not up, I don't think. I don't know. It doesn't look like it is. Hi, Chet. Don't, Tessa, I'm not gonna worry about it. EJ shaved? No. Oh, me, yeah. Come like that. Can we backseat Minesweeper? Let me see. Can we? Oh god, I never know how to use this computer. There we go. We can't. Wait. This is just pulling up a website about Minesweeper, not actual Minesweeper. Is there like a website? Minesweeper Online. Nice. I just want to play. How do I... There we go, chat. Let's see. Click that one. It's like... You hit the... Like, this means that there's one next to it, or one that can touch it, right? And that means that there's 3 that'll touch it, and that means that there's 2, but that... Okay, whatever. I'm just gonna click over here. Hi, drummer. 1, 1. Ooh, big one. Finally a compelling streamer and content. Diagonals count? Okay. No! Ruined. It's the distance to the mine?
No answer.
Alright. You okay?
I'm good. I'm good. Are you playing Minesweeper?
I was trying to find a fun game to play and I lost. First 4 corners first?
Yeah. Yeah, you gotta go to the corners. What are you, crazy?
Okay. 1, 2, 3, 4. I'm trying to remember how this works. Does that mean that there's a bomb 1 away? Or how did, like, can you remind me? What are the Minesweeper rules? Somebody told me to right click. Set flags. There's 1 bomb. Oh, that's how many mines are adjacent. Okay. 1 bomb touching the square. Okay. Start from a number that is a corner. The number is right next to the number is right next to its number of mines. Okay. So why do you sometimes get a bunch of numbers and sometimes you only get a couple? What's wrong?
Nothing. Minesweeper.
Listen, this is compelling content. I don't know what you want from me. You didn't have Kerbal up. No, I didn't even think. One second, chat.
You guys like that? Great. I need more coffee. You absolutely enjoyed wife cracking the whip. The engine, by the way, it was developed into the GE4. Oh, for the 2707. Interesting, Tessa. Most of us have been there. Yeah, it's just fine. NASA showed up to the IndyCar race with an RS-25. Ingenuity's off to a normal flight. Okay. Oh, neat. That's cool. Yeah, they did the helicopter on Mars again. Very nice. Yeah, I wanted to check that real quick. The YJ93. Let me just... I need to read about this real quick. The YJ93 turbojet was designed as the power plant for both the XB70 and the XF108. The YJ93 was a single-shaft axial flow turbojet with variable stator compressor and a fully variable convergent-divergent exhaust nozzle. Huh. The YJ93 started life as the GE J79X275, an enlarged version of the J79, with the 275 meaning Mach 2.75, the engine's target operating speed. This design evolved into the X279 when Mach 3 cruise became a requirement and ultimately became the YJ93. The engine used a special high-temperature JP6 fuel, and the 6 YJ93 engines in the XB70 Valkyrie were capable of producing a TWR of 5-to-1, allowing for a speed of 2,000 miles an hour at an altitude of 70,000 feet. The first engine went on test in September of '58 and featured advanced technology achievements such as electrolytically drilling longitudinal air cooling holes in the turbine blades. Oh. We're just learning all kinds of new words today. I don't hate what's going on in this picture. Yeah, Cosmo. Yeah. I mean, that's a monster of a freaking engine. I mean, can you imagine, like, I mean, it's what Hermeus is kind of doing right now. Can you imagine an XB70 with some with a high bypass turbofan? Could get pretty efficient. You'd still need a lot of power to get it up there, though. But electrical discharge machining, also known as EDM. Yeah, yeah, electrolytically drilled. So yeah, using electricity to machine stuff. It's pretty cool. There were proposals to turn the XB70 into a passenger plane. You literally just type in XB70 passenger. It'll show up in the concept pictures. Yeah. Pretty crazy. It's a big plane. I mean, those windows, you'd think those windows are like this big. No, those windows are about this big. I mean, if you look at the door, this fuselage is like CRJ 700 sized. It's pretty big. It's bigger than you think it is. It's basically the same jet engine core as the Star Raker. The J79 was a big deal, Tessa. That was... I mean, I could do an entire stream on the J79 jet. This was a game-changing thing. I mean, look, just take a look right here. 55. May of 55. This is... And the J79 was used for a very long time. And most jet engine design is kind of based off of it. Maybe not most, but the idea is there. It's just a staged axial compressor. Like, a lot. Yeah, most jet engines look like this nowadays. 55. Oh, okay. Also, why canards? Why can't we just get rid of those? Having 6 engines in the back makes it a little tail heavy, T-Man. There was a turbo shaft variant? The turbo shaft variant of the J79 delivers 15,000 shaft horsepower. What the hell? Okay, all right. Let's load up. Let's get back into Kerbal. 15,000 horse. Okay. That's a lot of horses. Yeah. It looks like a pod racing engine. Alright, let me equalize out the Kerbal audio. Get rid of that. Get the tunage going in the background there. Alright. We started working on the wings, or at least some ideas for the wings for Star Raker. Let's see where it gets us. Can I fit it in a Miata though? I think it's bigger than a Miata. Just putting it out there. The 707 and the DC-8 were flying in the late 50s. Yeah, Adam, it's kind of nuts considering, like, you look at that and you look at what a plane, like what a passenger plane looks like 10 years prior. It's just like, oh, okay. All right. Yep. Pod racer with a J58. I want to see that. That's Panther, that's basically Anakin's pod racer. Yeah. Anakin's pod racer has bypass ducts. They're basically SR-71 engines. Seriously. He opens and closes the little bit the bypass vents on the sides multiple times. They're Radon Ulzer 620C turbo. I'm pretty sure they're turbo ramjets. I'd have to go look at that one though. But yeah, Anakin's pod racer if you want that. But then again, Anakin's pod racer doesn't have an intake on it, which means it's not capable of going supersonic unless Star Wars figured out some crazy type of turbine technology where you can feed supersonic into a turbine. I wonder what car could fit a J58 in it in today's standard cars. Okay, I'm gonna get to work on this. Okay. All right, let's get the fairings figured out. I did take the engines off while we go and sculpt out the wings here. Let's see how this, let's see where this gets us. So, we started working on wing tessellation here. What kind of engines did that Slimo Sebulba use? I don't know, but he had something with some type of intercooler on it. That's what those things are. And in terms of why it goes, I'm not sure. There's some type of shockwave that's coming out of those engines that makes the noise. And also the scroony dopot Slimo. Alright, Antari, see you, buddy. Alright. Exactly that. The noise is the hover part of the engine. No, pod racers use repulsor lifts. At least I think. I was joking. Okay. Repulsor lifts are basically superconductors. in Star Wars lore. It's a superconductor. It's LK-99. That's what makes the ships in Star Wars hover off the ground and stuff. Like, that's why the pod racing engines can just sit there. It's because the repulsor lifts. Yeah, it's a superconductor. Or, well, kind of. That's the idea. Is that what makes the Matrix hovercrafts fly? The hovercrafts from the Matrix seem to use powerful electromagnets and Tesla coils to make a magnetic field that repels gravity somehow. I don't know. Django Fett seismic charges are the best audio in the movies. Seismic charges. Bow. Cool, I'll go with that. EJ, yo EJ, who's Lindbergh? What? Like Charles Lindbergh? Poetic license makes the Matrix things fly. Lindbergh is the boss from Office Space. Blue filed for this rocket name called New Lindbergh. I don't know. I've never heard of that before. Isn't that thing says it hasn't been, that patent expired. Charles Lindbergh is the namesake for that is Charles Lindbergh, the first American aviator to cross the Atlantic in his plane, the Spirit of St. Louis. A note in the Matrix that they're always depicted pushing off things. They seem to have a steep fall off. Not enough to do more than just barely peek above the clouds. Is that the same dude who crossed the Atlantic? Charles Lindbergh, yes. Yeah, Gary, we don't talk about that. What am I looking at? The outer skin of the wings farm. I'm going to farm, like on an airplane, if you need to take a panel off that's riveted, you'd get like Glicos, and you'd get the rivets out and then pull the panel off and then put it back and pop rivet the thing back in. This is the skin for it. I just make it out of wings because these, with this geometric shape, you can bend it around stuff. Lindbergh was problematic. You could do better in terms of the optics of that. Yeah. Dude, he was an asshole. The Nazis liked him. He's a piece of shit. Like, I get it. Thank you. I really think that needed to be inferred, but there you go. Okay. I'm gonna get to work, okay? Yeah, give me a second, guys. I gotta refocus. I was thinking about making a panel wing tessellator tool here. That might not be the worst thing to do. I just gotta kind of think about how we're going to do it. So with the shuttle panel tessellator, we were basically making 1 to 2 rows of panels to get a really complicated shape. I don't know, Chief. I'm kind of scrambled, dude. Give me 1 second. I'm thinking. Give me a second. All right, I'll say it out loud. So, if we were gonna make, I'm trying to think about the workflow for making tessellated wing surfaces. Doing the tessellated wing surfaces, you gotta kind of start with that, and then you move to that one, and then you move to that one, and then you move to this one, and then that one, and then this one, and then that one. So you go, like, in terms of messing with the wings, how I build was put wing 1 right here where you want to put it, right? And then put wing 2 where you want to put it, or put wing 3 where you want to put it, and then mess with wing 2. I'm not 100% sure how we're going to handle doing that with a tessellator. It might be better to just sculpt it and call it a day, but I'm not 100% sure. Like, I need to go look at the shuttle's craft file. Give me 1 second, guys. I figured out using the robotics in the game to make a machine that will shape the panels for you. Basically, it'll tell you exactly where to gizmo them, and that would be super freaking useful, I will say. But I'm trying to think about how that would all go together. Can you try a rough sculpt and see how it feels? Yeah, of course I can. This one has the tessellator built into it. Okay. I basically did the tessellation for that row, and this passive row being attached, I basically shaped it accordingly. I see what I did. At least I think I did. Let me just check this. Are these rotated on a 5-degree snap? If they're on a 5-degree snap, I should be able to figure this out. That's an absolute. I did that second row. I have to refigure it. Ugh, that thermal protection looks freaking terrible. Ugh. Really happy that I didn't go with that. Dragon, I basically have a good way to build the tessellator with panels, but I'm not 100% sure how we're going to do it with wings. That's kind of going to be a challenge to solve. Yeah, see, there's the upgraded TPS. See that? Now it's all one thing that goes all the way to the back. I can't believe we cranked this out in a week. I cranked out the panel tessellator in 1 week. And its design. That's pretty nuts, dude. Yeah. I know how I made this J-Speed. I know how to make that. You work off of each root part of the vein of panels here. Like, so that panel's attached to that one. That one's attached to that one. That one's attached to that one. You place this one first, and then move it out of the way, and then move the tessellator, and it'll tell you where to put the next triangle, and then you just shape the other triangles accordingly. Now, I'm not 100% sure, like in terms of like the vein of each panel, so 1, 2, 3, and 4. I'm not sure how I came to the placement on panels 3 and 4. What shape was holding, what makes them have that shape? Other than obviously like the shape of the shuttle. Was I trying to conform it to an edge, or did I just use the panel tessellator on this row? I don't think I used it on this row. I only remember using it to make that. I think we just sculpted the rest of these pieces. I need a VOD review. You know what? Dragon, what I think I'm going to do is give this thing a good old manual. We'll do manual tessellation, right? I'll sculpt it by hand. And then maybe, like, working through it will give me an idea for how I should go about doing this. I think that'll do it. Maybe. Okay, so where we were going with this is my sculpted piece has a 2-degree angle offset. So that's obviously 0 degrees. That's perfectly flat, right? And then it angles down at 2 back here. So there's no way to get this exactly at 2, right? I can manually sculpt it, but there's no way to get it exact. So, actually, all right, well, there's something that we could do. I can make a tessellator jig that basically shows you where a 2-degree offset panel would end up. So, like, I attach it here, it'll show where this needs to go, and that'll locate the initial position of this row of wings. And then we can do it over and over and over and over again until we get to the back. Because I'm pretty sure I'm using a 2-degree offset the entire time. But even if I'm not, we can, you know, it's 2 there. And I think it's 2 again. Yeah, and then it's 3 right there. It's 3 again. And it's 4 at the back. Now, the reason why I'm making a big deal about the angles, guys, is because if you have toggle snap here, right, and you do something like this, that's 5 degrees. That's a 5-degree increment. Okay. I'll just do it manually. I'll do it manually and we'll see where it goes from there. All right, so first row. It needs to conform to the fuel tank. So basically the first row can stay flat for the most part. I don't think I'll need any more than that, so get rid of that. All right, so... I mean, do we want this thing to conform down? I need to look at the wing shape there. Give me a second. Lockheed Star Raker. Or no. Oh. Rockwell? I need to basically kind of look around at the wing shape. That's in Kerbal. I know that's kind of a 3D printed one. This is the Italian guy that did all the renders of it. Yeah, Giuseppe De Chiara. Yeah, okay. Yeah, the LOX tanks would have been a little bit forward at the center of mass. Tank design there. There's the structure for the back. Vistas Sinistra. I like the Sinistra. Sinistra is, I think, left. Vista Superiori, top view. Vista Interiori, back view. Vista Sinistra's left view, I think. Interiori is front. Okay. Yeah, okay, cool. Thank you. Grazie.
Discovery, go at throttle up.
Hey, Matt, what's going on? 101 month resup plan. What's up, buddy? How are you? Nothing much, just working on photos and editing an article. Nice. How's you? I'm good. I'm having a little bit of trouble figuring out how I'm going to make this wing shape, but we'll get it. Yeah, the Star Raker is huge. It's gigantic, which is why I like it. It's a ridiculous project. Let's go back over here. I mean, yeah, the top of that wing is pretty much flat. Like, it's a pretty dang flat shape. All right, I'll just sculpt manually, I've decided. So let's Alright, so the first thing we do is we define that line, define this one right there. That's what we got there. So there's what's more or less what the back of the plane is going to look like. Now, this row for the most part, yeah, we don't really need to touch it. It's out here where this is going to start to get a little bit weird in its shape. That part I have blanked off because control surfaces. The control surface housing is going to go there. And the wing isn't going to be this long. I have my wing indicator there. So these are just excess. We'll cut them off later. Just put them there because they're better to have there. Getting more hype with Cities 2, each new dev diary? Yeah. It's pretty awesome, right? gonna be fun, man. I have a feeling you and I are gonna fall down the rabbit hole. Matt, I'm not budgeting anything for October. Like, everyone's like, oh, what are you doing in October? I'm booked. Totally booked. Just like for September, Starfield, I'm going to abuse the snot out of Todd Howard's game and see how well it breaks, and then you guys can watch me do that and either say it's awesome or it's not. So by the time the wing gets up here, the shape is a little bit different. It's more basically a straight shape. Like even if we're looking at the orthographic views here. These section views. I really wish we had more of these. So basically this shape needs to transition back to being basically pretty straight from what I can tell. The wings seem to stay very, very flat on the top of the entire system. That's the XB70. But there is a dip right there that we have to get right. Can you share the link to this PDF? Yeah. City Skylines 2, Wolfie, yeah, right? Well, what are we doing? We're booked. Yeah, no problem, cats. All right, so... Oh man, this is the worst time for this freaking to happen, man. Trying to get the gears turning, and they ain't going. It's not ideal. So that's I mean, we're at a 2-degree slope, so this isn't. I need this to be straight by the time it gets to the wing leading edge for the most part. So that means we have to have an average. It would be good to have an average out here. So that's 2 degrees tilted backwards. And by the time it gets out here, it needs to be 0 for the most part. Because it seems like from the pictures that I can tell, those are all pictures of, that's the YF-12. I need those for reference later. Good YouTube video, but yeah. That's about the XB70. It's about the XB70 again. Star Raker, here we go. It looks like from like Haze Gray's. Yeah, this shape right here, that's going to be a little bit difficult to make. Because it's, yeah, kind of helical. But by the time you get out here, you're out over the fuel tank, so it gets pretty straight. You know what? I don't want to watch the whole video again, but I just need to get some reference, and I'm gonna. This is Haze Gray Art's video. That's where that screenshot is from. I don't want to watch the whole video. I'll link the video in chat. I just need it for some reference. I don't think they fit in the hangar. Yeah, no, me neither. See if we can just get a good picture of the thing's wings here. Yeah, that shape's throwing me for a little bit of a curveball. This thing would have been ridiculous to see take off. Yeah, that... Hayes is pretty damn close, Foz. That's a pretty good model. It's pretty close to what those isometric pictures show in the PDF. Yeah, the wings kind of... The wings are flat on the top, but the bottom edge kind of... Like, it's concave, I suppose. Or, well, convex, maybe? Yeah, see, it's this shape. That shape's going to be a little bit tough to make. Just getting this shape down like that. All right, well. I know what I can do. I got an idea. Give me this. And we'll make some front to back angles here to get this shape right. Flip this thing over like that. And we can kind of use this as a little bit of a template. Right? More or less. More or less. Actually... okay. I think I got something. Alright, so... So take this, and then I'm going to get a small hinge. And I'm using the hinge... I'm not using the hinge for... This isn't going to be in the final design. I'm just using it to move stuff around. So what we should do with this, right, is I should move this basically to right at the edge of the wing. And then take the hinge piece, right, and move it right over the wing. And then if I do this a bunch of times, right... This will basically get us... Yeah. Hang on one second. This should basically get us, like, instead of... The I-beams will get us the exact... Yeah. There we go. And now, well, we could do one better here. Let me think. Oh, yeah, Alex, they kind of do, don't they? Yeah. That there, then that there, like that, and then one more, and that gets us all of our rows figured out. Okay, now get rid of this last piece. Give me one of those. Just so we can see where the end piece is. Now, whatever I move this to is going to be the angle that we're going to find with the wing. That's no problem. So now I should be able to sculpt out a little more of these lines. Get them a little bit more kind of on par with what we're looking for. So move this right here, for instance, right? What do we want this profile line to look like? That one, believe it or not, pretty much should be the same, right? What's the point where this shape starts really changing? It's pretty much right here. Right here is when we have to start conforming this back wing piece to the kind of boat tail of the entire vehicle. Look at page 32 of the PDF. Dude. Yeah, this part's going to be hard to make. I see it. How goes the Star Raker build? Also glad to catch you on NSF yesterday. Was it? Yeah. Well, we can only move these in 1 degree increments. I would need finer control with this. I don't think number input can go to the decimal point, Core. There we go. So that should plug in a 0.5 degree target angle. See? I use the cow controller to get fine control here. We might not need it though for this particular time. But that is a good way to do it. You may have this answered already. In Haze Gray's video, it jettisons the landing gear. How will it land then? It jettisons 3 out of the 4 bogies, J-Speed. So that's 2. So if we set that to 1, that's right. What's the next angle here? 2 again. just messing with this to see if we can get this kind of lined up. Alright, we can get rid of that. I don't think we necessarily need fine control on any of these. Let's just make this the pieces and call it a day. We'll kind of sculpt out where it needs to go. This way. See if we can get this right. Thanks, Mystic. Basically, I'm gonna make the longitudinal stringers on this thing. We're just gonna sculpt it out, and because we're working in sim, I really only need to sculpt it on one side. All right, and this should help me get my shape. We'll aim for splitting that beam, because that's basically where we started. Let's go here like this. That's fine. Now you... Yeah, that's good enough to get the point across, I suppose. And this guy needs to be... There we go. Alright. Now I'm wondering if there's a numerical combination that we can do to get this. And then, you know, from here we might be able to make a matrix of numbers that's going to get us what we want. We'll see. But using whole numbers might be able to get us where we need. Using random combinations of, well, not random, using combinations of numbers could get us what we want. And that might make this a little bit easier, not using... Yeah, see, this is where... Yeah, okay. This is where using the cal-controlled thing and getting decimal points might be a better idea, but it's alright. See, like, what did I do here? That one's 3. So this one is 1. That one's 1. That one is 1. That one is 1. Okay, what are you? That one is 3. Okay, let's switch that to 2. Yeah, I think we can use combinations of numbers here to get this right. Alright. Well, that last one ended up being 8, so let's make this 5 and see if we can do like 6. And lining, if I line the wings up with the I-beams, it'll give me the position that I need. And then it's just going down the horn and matching to the I-beams. The I-beams are basically showing me where I need to place the wings before anything else. So that one is 2. See, this one is 4. I don't necessarily want 4. Let's switch this back to 2. What is that one? That one's 5. So obviously we don't want the wing to go in like this and have the wing go down and out. So this number needs to be either equal to, for the shape that we're doing, or greater than. What angle did we end up going with here? That's 6. I wonder if we can... Yeah, see. These numbers should be... Down here, they should be descending as we go further down the stack. And up here... Actually, yeah, the numbers all should be going down, not greater than. It needs to be less than. I think. 5, 5, 6 to 4. Okay, so let's compare here. That's 1 to 1. 2 to 3. No, that needs to either stay the same or go down, because that's the shape we're trying to make. Hey Matt, what's going on? What's this one? 5. That one's set to 4. And what's this one set to? That one is set to 2. That one started at 5, went to 5. Bet I can watch it work for a little. This job sucks. Yeah? My brain is trying to think of a mathematical way to solve this problem. There's got to be a way to get, there's got to be there's got to be a pattern here, right? I mean, eyeballing it does work, but yeah, Cat, exactly. That's kind of what I'm looking at, why this really isn't getting me what I want. Maybe we could start with a definition line right here. For the most part, by right here, the wing needs to be flat. It needs to be flat. That's the shape. The shape is flat. So that would mean that from here, and you know what? That's a good point. That's probably going to give me a profile that I'm looking for. So if we set this to 0, right? And we set that to 0. Look. Oh boy, this is the boring part, but this is going to pay off if I sit here and stare at it hard enough. Yeah. See, this isn't the whole thing, though. That's a weird shape, and that doesn't look like it. What's going on here is the wing shape is changing. This is going down like that. No, it can't be. It has to be flat. Right? This has to be completely flat. There's some kind of weird optical illusion going on here that I'm not getting. Yeah, it's not entirely flat there. See, like, because what I'm thinking is that if you look at the top right of these engines, right here, and top left right there, they're not aligned with the top of the wing. So it still does curve down just a smidge, but it's not much. So what happens if we take this piece and we just send it back to where it needs to be, right? Send it back up here. And then set this to like 1, 1, 1, and 1. Where does that get us? Doesn't get us very far. Look at the bottom left of page 5. Last two things for you. One, it seems like the wing tanks were arranged route to tip, and more usefully too, page 5 has a low quality. Yeah. Yeah, I see it. Man, are you going to fly to the moon in this? I don't think it'll make it to the moon, Namio. I don't think it'll make it there. But it'll, hopefully, Jeb willing, it'll make it into space. Okay, let's try setting this to 2s across the board. Bottom left of the figure is the root shape. Yeah, it does curve back. That's the root, so that's right here. Yeah, I get that. I'm trying to figure out these areas here. YC, I forget what it said. I forget what that means. But it's something about airfoil shape, I think. Now, see, this pretty much gets us where we want. That's actually not bad at all. That gets us what I'm looking for. So this is basically one. It's called Star Raker, not Moon Raker. Yep. I'm pretty sure he used the same PDFs that we did, RJ. One, two, 2, 2. Okay, I got an idea. Give me this right here. Let's just, the heck with the numbers for a second. That's the shape that I'm looking for, more or less. That's where that wing needs to end up being. That's where this point needs to go right here. And then that'll figure out more or less where the outside channel of our engines is for. But, yeah, we might need to do some modification there on this piece to get it right. But give me, maybe I'll move the nacelles out a little bit more. I don't know. Or we'll just have a little gap there because the width of these things doesn't necessarily match the proportions, but it'd be easier to work around the wings than it would trying to match the wings to said proportions. So we'll figure that out in a second. But all right, so get me the original control curve. To go right there, and then take that and just flip it out of the way and get rid of that one. now I'm going to move this thing into its place. Like that. Now we'll match the I-beams to these, more or less, as best as we can. It's just, yeah, with the wing tessellation, using these complicated shapes gets a little weird. Okay, cool. Now, for a second, I'm going to get rid of these. Now, we have that piece right there. That's for the strake diagram. That's the lower curve. That's the... Okay. Take this piece up here like this. I got an idea. I think I can figure this out. So move this here like that, get this piece there, and then make sure that the hinges are all more or less lined up. Procedural radiator parts for KSP2. Yep. Yeah, like Captain Crush was telling me about it the other day. I forget what it is, but my brain is not working very well right now, so... Yeah, I was going to say, Rain, that's not anything new. We should... Hopefully we're getting re-entry heating soon. Seems that Starraker jettisons the undercarriage after takeoff. How does it land? It doesn't jettison all of its landing gear, Vertex. This set right there stays on. It jettisons the others to save mass. Landing. I'm alright. Landing gear subassemblies in Kerbal are not that high mass. So I'm just going to have it carry all 4 landing gear. It'll take off on 4, it'll land on 2. Or 1 set. You know what I mean? YX is the chord ratio, the percent thickness of the airfoil section compared to the length of the chord. YC equals thickness divided by chord length. I wish my brain was working better right now, because that makes sense. It's just I'm not sure how that applies to what we're doing, and it's one of those things where brain do good more what, like... Alright, so move this all the way over here, okay? So, let's see if we can... that won't line up exactly. It's close enough. Alright. That's good enough to get the point across. So, we need to bridge the gap from there to there, right? And this should be very simple. That's 2. That one is 1. So that means we have how many sections in between? 1, 2, 3, 4, 5, 6, 7. And that actually will get us our fraction number for this, more or less. We just need to divide it by 7. So the difference in angle, right? 2 to 1. So we have 1 degree between here and here. We need to divide that into 7 parts, and that will get me the rotation per. And then we just need to average that number to that number, that number to that number, that number to that number, and that should get us the exact shape we're looking for, more or less. Let's put that theory to the test, shall we? If I take these right here, don't want to move that. You use the panel machine today, or it's all by hand? The panel machine is hard to get working with this because these are wings and not panels. It was really designed for that exact shape. Sile, I'm kind of trying to see if we can come up with a better way to do this. It's not necessarily going to be a panel tessellator, but I should be able to use a little bit of math here, like basic math to get this right. I'm trying to just sculpt out the back wing here, and I think I can get it. I think. Maybe. I'm actually kind of prototyping this right now because I don't have like an exact blueprint here, so we're going to kind of extrapolate data. So now let me think. There's got to be a way to do this right with the Cal controller. We can average with this thing. Okay, so let's get the calculator. So 1 divided into 7 parts is 0.1428. That's not really that whole of a number, and Kerbal is using float, so I don't think it's going to understand that. Let's use 14285. So go in here, open the editor. This is, let's just say controller 1, right? So we need to get an average here. From there to there. So this one needs to be 2 minus 0.14285.
Discovery, go
at throttle up. Pacey Big 50. Thanks, man. Okay, maybe we can work our way back. It'll be easier to do that way. So if we set this thing, what's our default? Our default is 1. So this would be 1 plus 1.14, right? And that would be that thing's default position. Yeah. Okay. Now, what I could do is copy this curve, right? Paste that here. Well, paste all of them here. It's not going to look exactly right, first of all, but it'll get us close. So, because we can plug in the decimal point, hey, it took to the 5th decimal place. Not bad. Okay, so 1 plus 0.14285 1.14285 plus 0.14285. 1.2857. That's our number for the next one. We go in here, paste that. That gives us a little bit of an average. Yep, there we go. Plus 0.14285. 428.55, that's this one. I know there's probably a better way to do it, dudes. I'm just not doing the best right now. Give me 1 second. You can't control these things down to the decimal place, which is why I'm plugging them into a cal controller, Matt. Yeah, controlling them down to the decimal point doesn't work, except if you plug it in via a cal, which is, yeah. Plus 1.71425, so that would be this one. Bar Baker. And now the number one spot here, plus 0.14285. Oh, 1.71425 plus 0.14285 equals 185.71. Copy that number, go here, paste that number. And then 1.85 plus 1.4285 should equal 2. Okay, cool. We got the first row figured out. Excellent. Now, let's go. Controller 2. Same exact thing. Let's go in here, and we gotta average the points through, but controller 2 has this one, this one, this one, okay, 7 fields to put in. What's our average? What's our distance? So this one is going from angle 2 on the far outside one to here. It's the same. It's the same? Also, these ones have to be offset. Offset so they're on the edges of the intersection points of all the wings. That's the only way to really get this right. Even the ones on the outside. Well, that one doesn't seem to change too much. Which, yeah, you're not... I mean, if we got variation here but no variation there, that's not going to look very good. You're not going to look very good. Oh, you got me. Oh, man. I'm just not really... I mean, the patterns that I'm using basically say that this should be correct for all intents and purposes. I noticed that each one of these nodes have to be back a little ways. Okay. Cool. Hey, that's what's going on. Intense, yeah, like Elon tents. We're in a hangar. Hangar is just tents with more metal. Yeah, that's science. You like my tessellation? Nice, nice. It's just a metal tint. Yeah, well, we're not getting the variation. There seems to be no variation there, which I suppose that makes sense. I just don't like how we had variation here and not here. So, maybe I'll make variation here. I mean, the angle that I put my jet engines at was just guessed, so this is just kind of a rough estimation. This should get me more of what I'm looking for. 1, 2, 2. Comparatively. Yeah, we're gonna get super big variation up here. But this angle being, see, I gotta set this one to 3 and we gotta set this one to 5. That's how that needs to go to get this correct, because this is the back of this is kind of parabolic almost. So even like getting this to 3. Yeah. That'll do it. Cool. All right. So, I mean, 2, 3. Where does 4 get me? No, this last one needs to be 5. Yeah, that's how you're going to draw a parabolic arc. I mean, I'm way too tired. I did an entire RSS Mars lander. Then instead of returning to Space Center, I reverted to Oh ho ho! How are you going to curve the wings on the other axis? 95, it would put hinges between them on this axis. I'd put, you know, I-beam, hinge, I-beam, hinge, I-beam, hinge, so we could make the wing go down, but the wing seems to be pretty dang flat. The adjustable, yeah, the adjustable buck. That's right. Yeah, it makes it pretty easy for the top. It's the bottom wing that's going to be a little bit difficult, because the whole thing is shaped kind of... It's kind of like heat shield shaped almost. The fuselage of the plane goes like this, and then it goes out, and then at the very wingtips it kind of curves up again. The top, this is actually going to be the easy part, which is why I'm trying to see if I can come up with nice ways to do this, because this is the easy part. Hey, Gall, thank you. Yeah, I appreciate it. All right, so what's the difference here? The difference is, so we're 2 to 1 again. So if I open this cal controller, right, we can do the same thing again. Then we open this cal controller, right? We can copy 1 to 1. So take this, copy it, paste it over here. Next one, copy it, Paste it over here. That's the same, we can use the same numbers. Alright, cool. That's the same average. Nice. So now let's go to controller 3. That actually ended up being pretty easy. Open the editor. Go here, like this. Now we need to do 1, 2, 3, 4, 5, 6. Yeah, yeah, that's right. Okay, cool. Now, what is our average here? So we have 2. A 2 difference. So 2. Wait, would these numbers be right? Yeah, 2 divided by 7. 2 divided into 7 parts, which gives us a, or no, yeah. .28571. There you go. It's double. It's just double that. Okay, cool. So if this one's going to start at 2, and we're going up to 3, so we take this, paste that number there. 2.28571. And now because we plugged it into a cal, oh, it rounded to 2.29. See if we can copy the figure directly over. Oh, it did. The cal controller just rounded. Copy that number. Plus 0.28571. 2.57. There we go. Select that, paste that in there. Okay, that worked. Cool. Now let's just do the same thing again. Plus 0.28571. 285,713. That's this one right here. I know, guys, once again, if you're looking at this and going, wow, that's really a really bad way of doing it, I have a feeling there's probably a better way to figure this out. I could probably use the average curves in here to figure it out correctly, but I'm brute forcing it because, yeah, my brain isn't working too well right now. I got a lot on my mind, but we'll get it, don't worry. Plus 0.28571. 3.141592637. Bad? This is impressive. Oh, alright, well that's good. $342.85. That's this guy right here. $371,426. Gives us 39997. Cool. All right, there's your average right there. And now we need to go to controller 4. These curves are going to get a little weirder as we go further. Open editor. This is controller 4. What are these robotics for? Landlord, it's going to mark the position of the wings. I'm trying to make a really complicated shape here out of triangular wings, and these will help me. These are basically helping me mathematically know where to place each wing. I'll freehand to this jig in a second. All right, so we're at 5 over here and 2 over there. So we got a 3. We have 3. 3-degree differential. So we need 3 divided by 7. .42857. Okay, so all right, so we need 2 plus see, yeah, that's not going to plug. So what I need to do, excuse me, what I need to do is go to controller 4. 1, 2, 3, 5, 6. Okay, now we need to take that number. 2.42857 plus 0.42857, 285,714. That's this node right there. Plus 0.42857, 3.28571. Okay. Plus 0.42857. There we go. Copy that. Mark that position. For 14285. Last one, plus 0.42857. 457, 152. Okay, there's your shape. Just press equals again. Yeah, I'm sorry. I forgot how to calculator. Like I said, I have a lot on my mind. I'm trying to focus for you guys as best as I can. Thanks, CryptoSlang. Please excuse my momentary dumbness. Please excuse the dumb for a second. Alright, so let's sculpt the first wings here to the shape that we want. First row. That's pretty much where we need to be. So now that we have all this, I'm going to save my work first of all. And what we can do is we can add even more. We can do this same type of thing again over here to sculpt out the rest of the wing. We're not going to need that many more. 1, 2, 3, 4, 5, 6, 7, 8 more, maybe. You're doing the best you can, yeah. Yep. Now, what would really be nice is if I had a way to mark this wing correctly. That can give me basically a spot where I need to go. Where that wing needs to be, but see, that gives us the exact position. That would be really nice. Rather than freehanding it, because how the see this is where a tessellator is. I might need one, because how the heck am I going to make a freaking how am I gonna eyeball a 0.14 change in rotation? It flies into space, crustacean. So how big how big do you want the wings? Yes. Yeah. RFK Racing is becoming one dangerous team. Okay. Wait a minute. Hold on. Yeah, I'm just not 100% sure how I'm going to line that up exactly. Yeah. Attach the main parts to a zeroed out end of sequence on the controllers so they bend at the angles you need when you put connect jet back to start. I can't talk, but I think this can help. Attach the main parts on a zeroed out end of sequence on the controllers so they bend at the angles you need when you put the cow controller back to start. Well, King, where I'm kind of at is, unless I want hinges all buried into my wing design to get the exact decimal point rotation, kind of boned. I really don't have a choice but to eyeball the damn thing. Let's just save our work right here, and I'll try to eyeball it as best as I can. Yeah, there's no... I don't really have an indicator here. Whatever, we can make it work. Okay. I honestly think that angle is so ridiculously subtle that I don't even need to adjust the secondary parts. And if I did, it would need to be basically that. That also needs to be out there. We'll just leave that for now. Just join, what are we making? I'm building a very complicated wing shape. No, okay, it's not bad. There's a better way to do this. I know there's a better way. I might need to sleep on it, but we'll... Not right now, not right now, not right now. Don't worry. Make the god the exact same height as the wing itself and visualize the Z fighting. The problem is that the top of the I-beam doesn't absolute snap to the top of the wing. That's about as close as we're gonna get. But that actually, you know what? That might be good enough, Cratch. We'll see. That actually does help with the visualization a little bit. Getting a little bit of a better guide here. Cratch, also, thank you, because that observation that you made about that tells me that what I'm doing isn't entirely bananas. PDF, they had a few cross sections, connected them with straight lines towards the tip. Maybe you could do that as well. Yeah, I think I'm onto something here, Aqualex. I'm just gonna keep doing this, okay? There we go. Cratch, I think you did it. I think we got it to work. I think that's the key. Now let me get this one and see if we can align that. For the most part. Actually, that's the one that needs to be aligned, which means we might have to redo some of this a little bit. Glad it worked as it did. Yeah, it's not bad, dude. This is pretty good. I was able to get the wing angles that I need. I might do another detail pass on this just to get it right, but this is actually pretty good. See, like this one right here, see how we're a good leg up ahead of that I-beam? This one, the rotation point needs to actually go down, I guess. Like, it needs to be right here for this to get right. Which usually you shouldn't do that with the wing tessellation, but it did, yeah. That did, for the most part, line everything up. Looks good. Okay. So now what we got to do is move this up to the I-beam right there. That gets you the position. That would also mean that I need to move this piece up. Has this build been more challenging or less challenging than Venture Star? Less. It's not that bad. It's not as bad as Venture Star. Venture Star was tough because you're building the entire freaking pad. I think I screwed up by moving these. You're not supposed to move these up and down. It's rotation. Rotation is what gets tessellation to work correctly. So instead of that, I should have done this. And then we can just take this piece, take this next one. I screwed this up. I screwed it up. I screwed it up. I screwed it up, but I know the workflow a lot better now. I'm gonna have to remake it. Guys, yeah, gotta remake it. It's okay, remaking it doesn't take very long. Well, the notes are these things. The notes are the controls, weather guy. No translation, though. Translation always screws it up. It might be a good idea putting I-beams this way to get the profile as well. Basically, make a really, really more advanced, like adjustable buck, I suppose. I can. There's a way to do this with a panel tessellator. Man, that thing was cool. I can't believe I thought that thing up. Now my brain's hurt. My brain hurts trying to think about what I was doing. Oh yes, just I've forgotten how to open up my drink. Rest your brain for this for a second. The last thing I need is a distraction, but also llamas. I've had a recurrence of my drinking problem. That's right. Alright. This is gonna hurt me more than it's gonna hurt you, Chad. Ugh. So, all right. Get rid of this, get rid of this. This piece needs to be attached to that one. This will make this easier with the wings because that's where the control node is. Like basically where when I go to rotate the thing, that's where it ends up. All right, cool. So now we take this. Flip this over like this, go in here like this, and then move that into position. I'm sorry that this is taking so long, guys. There we go. last control node. Yeah, we'll leave that like that for now. We're not gonna, all right, so now we'll do this as we go. So that's all set to grandparent part. Okay, cool. So now check this out. Let's go here like this. Obviously, we're gonna copy this piece. That's the right position. Now, the real question is, do we go further back with it, or do we try to sculpt this piece? I think absolute snapping everything would be... Yes, I think that would be best. Yes, hi, I'm looking for Victor Maitland. Okay, we don't need this back row, so get rid of that. All right, cool. Now we're aligned. So now we do what we just did before. Basically rotate this to where it's coplanar. And this is the only translation you do, if I'm remembering this correctly. If I'm remembering like how to do this right. This is the only translation we really need. We shouldn't, in any other point in the design, need to use translation unless it's like a really weird edge, and it needs to look different. All right, cool. So now let's move that one down into position. There's a freaking bug in front of me. Before I go, I wanted to say one thing. The Super Cop story was working. Y'all fricked up a perfectly good lie. You fricked it up. It's alright. The Super Cop story was working. I don't know why you do that. Screw up a perfectly good lie, man. Still haven't figured you guys out, Clayton. Nice punch you got there, Taggart. Okay, so from here on out, it should be rotation that does this. So, like that rotation right there needs to go to there. This rotation needs to go basically to the underside of that I-beam. This one needs to go to that as well, right? There. And this one needs to translate like that. There. Number 4 comes out next year. See these little minute problems that I'm having? The panel tessellator solved that. It solved that by basically making one at a time. So like I started out here, and I would make that one, and then that one, and then that one, and that one, and that one, that one, and we'd move it incremental. We'd move it incrementally. Can't be that easy. It can't be that easy. Can it? Yeah, but how would we translate degrees rotation here? Well, actually, we could just take the increment. All right. All right. All right, hold on. Hold on a second. See, with the panels, you have a control point on the surface here. This is on the opposite side of the dang thing, and neither of these are lined up. This thing's control point is
Discovery,
there.
go and throttle up.
No. There's no way. No, they're not. No, they're offset. Okay, cool. That's what made that kind of easy. It's the fill panel where we're going to have an issue. All right, get rid of it. Get rid of it one more time. Yeah, we'll make the... We can do it that way. That's fine. All right, I'll try for it. I'll try for it. Hey, Crash, 70 months. Thanks, man. We'll go off the master node of the jig piece right here. I can't believe I visualized this stupid thing in my head. Part count so far, it's 1,097, but that's not, most of it is structural jig pieces, dude. What the frick? Oh, that's for building space station modules. Nope. 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 I thought I sub-assembled it. The protractor prototype. There it is. That's it. Does it work? It looks like when it was sub-assembled, it erased. Chill. I know this isn't the most riveting content right now, but the protractor prototype doesn't have any, none of the cow controllers are bound, so I really can't see what it's doing. Okay, one of those is rotation. That's the rotational controller, and then there's rotational length extender, so that would be master length extension would be both of them. All right, hold on. I should be able to rebind this. I just got to figure out how the frick I did it. Could you take where you got the calculator from, delete everything else and save it as a different craft file and merge it with this one? Subassembling it might... yeah, Jack, yes, we can do that, to answer your question. Yes, I can do it. I don't know what this does. I forget. I need to... If I understand how that works, I'll get it right. Give me 1 second, okay? So, I have my master length extension, which extends both of them, right? And then the datum extender is the bottom piece to figure out spacing. That one's to figure out the spacing, okay? This is the rotation extender. And then this one is the angle controller. Okay, so getting the spacing right is super important, but forgive me if this was said, but did Scott Manley make this thing too? I don't remember, Denny. Maybe he's probably tried it. I'm not the first one to do Star Raker, and I will not be the last. Dude, look at how crisp that is. Was I on my game that day or what? And we engineered this in a day. Look at that. That looks seamless. There's no seams. The panels are perfectly butted up against each other. It's freaking beautiful, dude. And that's how I made the shuttle strake, see? Look at that. Perfectly, like, oh. Man, it's nice. Alright, so I had rotation, I had a datum extender, and the triangle piece is definitely there for a reason. So that gold triangle, right? So let's try to figure out if we can make one of these things. So what would I need to do? We need to rotate the wing. And the wing needs to be on, because if I was doing it with panels, right, it's on the panel's rotational axis, right? So we need to put it on the wing's rotational axis, this one right here, right? Because we should only really move the wing this way, right? All right, take this thing and put it over here. So how did let's try to make another one. Another one. I'll use the same thing. It doesn't really matter. Give me a servo. Similar idea. And then I believe I made these things telescope for the length of the strake, right? That goes the length of the strake. Okay. We're going to need to make this go all the way out to here. All right, so let's get a length measurement. We'll use 3P6 hydraulics, 3PT. So the way to do this and make it so the hydraulics can move like front to back like this, like get the whole length, right? Because you're obviously not going to get it with one hydraulic. Right, so that one needs to start right there, because that's where the telescoping part is, right? And then obviously, like, we put this here. I'll show you how I do this, fellas. What's the current mass? It's over 1,000 tons. I don't know, maybe that would be enough. Alright, see now having them kind of clip like this will get me total extension. Like, there's no, the housing is not being used in our final extension measurement. That's why I did that. It's basically the same way that I make the gantry cranes. So that's enough right there. How many? 7?
Discovery, go at throttle up.
Hey, Jim. You! Almost a century. 98 months. Thank you. 1, 2, 3, 4, 5, 6, 7. Alright, let's just grab this one over here. Let me make a telescoping cylinder that's 7 of these long. Get our exact measurements. So, good way to do this, make it nice and compact, is to do that. So take this, rotate it once, 5 degrees, absolute, snap back into position. Do it again. Take the next one, rotate it another 5 degrees, absolute, snap it back into position. That's 3. Take another one, do the same thing, 5 degrees rotation, back into position. Okay, that's how I did that. All right, cool. I got it, but we got to do something first. So, do this. 1, 2, 3, 4, 5, 6, 7. All right, now, okay, we'll use this for our master node, right? Take this, do that.
Discovery, go at throttle up.
Now we need to move this to our, so it's in the default position, right? There. Hey, Bobby. Bad info, Bobby! Alright, now I'll just transfer the cal controllers. This is the master length extension right there. Take this cal controller, go in here like this, and then master length extension, target extension, target extension, target extension. You guys know where this is going. I just need to make this thing telescope. But see, stacking these things on top of each other means that my 0 position is over there. I need my 0 position here, and I need something that can extend seven of these long, because that's long enough to get the entire wingspan and then some. Alright, so take this, set that curve to maximum extension, copy it, paste, paste, paste. You know where I'm going. Okay, paste, paste. Okay, cool. So, whoop, whoop, perfect. Done. That one is set to 72, though. Why would I set it that way? No matter. So now that we have a cal controller working for this, now you take this, rotate it 5, gizmo it back, take this one, rotate it 5, none of this stuff is going to be on the final vehicle. I'm literally building better editing tools out of parts in KSP. Okay, so now take this and then make a test ruler with it. Waycrush, hey EJ, how's KSP going? I was curious because this is KSP 1. Ooh, does that count, chat? I'm not sure. Does that count? I'm waiting on more patches for KSP 2. Basically, I need to scratch the itch of doing crazy, super, ultra precise KSP shenaniganry like this, and KSP 2, we can't do it just yet. It counts? Alright, cool. So, actually, it's been rather low today. That was the 2nd or 3rd. I forget. Yeah, Waycrush, just give it some time. I'm just waiting on the patch. What I like to tell people is that KSP 2 needs a little bit more time in the oven, that's all. Just give it some time. It'll come around. Okay, so now I need... That's the rotational length extender. That's the datum extender. It looks like I didn't have the datum extender. Angle controller. Alright, take... So that means if I take the angle controller and we set it to 360, it's straight up. I don't know why I set that to 720 on the maximum, but it's okay. Why doesn't this one have the datum extender? That's really strange, but whatever. 3PT hydraulic. That's 20. We'll just set this one to 20 as well. Cool. Okay, cool. Rotational length extender is set. Okay, X that out. We can control it from here, right? Cool. Okay, so now do the same thing. 5-degree rotation, absolute snap back. I think I got this. So where I'm trying to go with this is that I'm kind of hoping that building a replica of this that's designed to scale around wings instead of scaling around panels will basically get me to figure out what the heck I was trying to do. Clip that into position. Take this. Take our rotational angle controller and set it to 720. Okay. Hey, Rocket Guy. How's the build going? Is this a door mechanism? No, Lulz, it is a wing tessellator. For the shuttle, I had my panel tessellator, right? This is a wing tessellator. I have an idea about how I wanted to make the shape, and I essentially made stringers. And then we did some math to figure out the differential angles between where like the middle profile curve and like out at the end of the nacelle profile curve. And there was such a like really, really small degree of rotation. There's no way I would have been able to get it right with freehanding it unless I have some type of jig. And that's what this is. This is a jig to help basically overcome the small angles. Think of this as a machine tool that I'm building in Kerbal. top tier. Thanks. Something is weird going on with this. I don't know why it thinks that that is center. That's not. Okay. Now we just need the datum extender. I'm not sure how the heck I did that. Let me save this one more time and just get rid of the stuff that we've already made. I just gotta go look at the other craft file real quick, guys. Give me one moment. I don't get time to watch a stream that much because of the time zone, so wasn't sure what state KSP is in. Oh, okay. There you go. Yeah, no, I got you, man. What does the datum extender do? Okay, the datum extender is that one. What's the difference between this and rotational length extender? Angle controller. What's this one? Master length. Oh, that's where I screwed up. So, the one that rotates is the one that has the triangle attached to it. That one is the bottom one. That one doesn't rotate. Top one does rotate. Okay. 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 I see what I did here. Most definitely I refunded it, which felt like it tore a portion of my soul out. You want to get the game when it's in a better place. I know, man. Yeah, I know. It's tough. Like, I think we should be getting re-entry heating sooner rather than later. And when we do, I'm giving it another stab. I want to play it. I really want to get, I really hope that KSP gets to the point where I could do stuff like what you see on the screen in KSP 2. Like, I really just kind of want the same exact editor in KSP 2. And yeah, that's it. Toasty, what it do, bro? What it do? How you doing, buddy? All right. So what? Why you forget? Why you spaghetti? Whatever. Datum extender was in the wrong cal controller anyway, so go here. I'm doing all right. Yeah. Dealing with some RL stuff right now that's kind of messing with my head a little bit, but other than that, we good, man. Get rid of that, get rid of that, get rid of that. All right. Oh, it's... Dude, don't worry about it, man. I'll be fine. I'm just... Yeah, sometimes you get curveballs and it kind of... You're just like, oh, alright, that's cool, I think. Let's just move that out of the way so I don't get confused. So this is the datum line extender right there. We need to... Is there any way I can select all these? No. Nope. Gotta just do the work over again. It's okay. There we go. Wish there were YouTube playlists to watch as a series. The stuff you do in KSP is amazing. I remember watching you do the whole reusable first stage stuff, blew you away. Thanks, man. Yeah, wait, Kirsch, I know. I've seen you. I've seen you in here before, dude. I appreciate it. Thank you for the kind words, man.
Discovery, go and throttle up.
Okay. That's good. So make sure that nothing is in the master length extension piece. There's nothing in there. Okay, cool. So now what I can do, save this. Whoa, I just got gnarly deja vu. I think there's a glitch in the Matrix chat. Whoa, that was weird. It might have been because I literally just made this, but no. I had the same kind of thought process when I was building this because I wasn't sure of building it the first time if it was going to work. When I built it, I was like, is it really... Do I really need another master rotation or master length extension on top of the datum extension? I remember thinking that with the other one. I remember thinking that with the original tessellator, so... The datum extender play position needs to be bound here, and the rotational length extender play position needs to be bound here, and those need to go like that. Copy the curve, paste that curve, so that moves both of them. Perfect. All right, cool. That is an exact copy. That's an exact copy of the tessellator. There is just one more thing. I need the wing. We need the wing as our structural piece. So type A wing. And now I need to move the type A wing so its point of rotation is exactly on the crisscross. There. Just like that. Actually, oh, balls. Under the black cat, was it the same cat? Hey, Barrelicious, 68-month resub. Thanks, man. Okay, so I'm noticing something here. When I was doing this to, like, with panels, the panel edge absolute snaps. At least I think it does. Yeah, see? The edge of the panel lines up perfectly with the strut. Oh, that's gonna be weird. You probably already explained this, but... this is the thing you use to make perfect curves, right? How does it work? Natalie, I don't know. I forget. I'm serious, I forgot. I forgot how to do it. I'm trying to figure that out right now. I'm not even kidding. I don't remember. This feels like the Born Identity or something. I don't remember. The numbers, Mason, what does it mean? I don't remember. Natalie, I honestly don't know. I swear, I'm close. I'm close to getting this right. Once I get it right, then I'll let you know. Oh boy. All right, so let me, I gotta check something, okay? So, with the wings here, how much do we need to move it? So, 10, 20, 30, 40, 50, 60, 70, 80, 90, 1 meter, 110, 120, 130, 140, 150, 160, 170, 180, 190. Yep. 100, so 1.9 meter spacing here. So that right there should work. That should be fine. We just got to remember that the strut is not exactly aligned to the edge, but that's okay. All right, so yeah, Maelstrom. Well, it was like a year ago, so please tell me we can do a test flight tonight. Curtis, it depends on how quickly I figure this out. If I can get this right, dude, we'll be able to just belt out segments, no problem. But yeah, see this shape right here, the I-beams? That's a complicated shape. Yeah, I'm trying to make this shape out of these wings, and we should be able to do it. But there was a way that I could precisely measure angles to get it like perfect before. I just got to remember how I did it. Today on how they do it, plumbuses. Everyone has a plumbus in their home. Because you can use triangles to make different shapes. Wait, why does that do that now? Why does it line up perfectly now? What the oh, that's... Oh, it's perfect. Okay, so, how are we going to do this? Let's take this one, for example. Let's take this first row. What's our controller spacing difference here? We would need to look right here at, no, hey, spaghetti. No, this one. One point, so it's 14285, okay. I gotta write that down. Yeah, I'm doing it this way. Shut up. It's not funny. It's science. Okay? That's my first rotational increment. That's my first rotational increment. 8675309. Damn you, Tommy Two-Tone! Alright. So this needs to be our zeroed position, and we're gonna need to go that way. I'm gonna switch this down to 180 degrees of rotation. Because that's all we're really going to need here. That doesn't need to go that far. So let's set our min value as 90. Actually, setting max value to 90 and setting this to 0 might be what we want. Yeah, there we go. Okay, and now the wing, this piece right here, wait a minute, why are you doing this? So now this should move independently, and that gets us our wing rotation. .90 spacing increments. So this is your translational movement, and that's your rotational movement. Okay. Now, one thing that I'm really trying to figure out now is that why are these two not like completely set? Why are these two not? These two should be perfectly parallel to each other, but they're not. Why? Those struts aren't going exactly through each other, and I'm not 100% sure why that's doing that. Is the strut set to absolute? Is it set to absolute down here. Alright. Let's take this and then put that right there, and then just absolute snap. Why are we getting an offset here? That's weird. That shouldn't be doing that. I hate being imprecise like this, but there. All right, that's fine. Save. Don't touch it. Okay, so now we're gonna test this. We have our rotation. That's the axis of rotation that we need to rotate every increment. How did I decide to do this? Okay, so straight edge forward. So the point of the triangle, the side B is the side that's pointing towards the front of the vehicle. So we're at B in the hypotenuse right there. So facing forward. Like this. So, because we're making the wings this way, I'm going to turn the entire tessellator and just put it this way. So now, let me make sure that the wing is pointed in the right spot. See, yeah, that's why I did a 360-degree rotation here. So set that to 0, set that to 360. Yeah, that's weird. Yeah, okay. I'm stupid because we're offset 180. Yeah, there we are. Cool. So that's gonna. I'm going to set this at minus 90. We'll do 180 degrees of rotation, which will give us positive 90. All right, cool. Positive 90 there. And then I'll set the main control to 180 degrees. That means whatever we're plugging into the cow controller, right, will be our angle offset. Cool. All right. Now, if we absolute snap this back into position. I know you're busy. I just wanted to say thanks for Sunday's coverage with NSF. Hey, yeah, Duel, no problem, dude. Fun stuff. Here's to the next one. Thanks, man. How's things going over there in OK, man? Everything good? I just got to make sure those are exactly coplanar, and they are. Perfect. All right. Okay. Good, man. Just another day. Fired up KSP. I knew we could count on you to be playing it and join the day. Yeah, I got you, man. I got you. All right. Okay, so let me think. That gets you your rotation. Or that gets you extension. That gets you your rotation in decimal. The datum extender is just there for marking where the next piece is. Got it. Okay, cool. Move the datum extender back. The master control can stay there. That's our angular rotation. And our increment is 1.9. All right, Natalie, if you're still here, let me see if I got this figured out. So this is the wing structure that we're gonna make, right? I'll set it to grandparent part. That's the datum piece. What I'm going to do is just put, I need a way to mark this thing. That's the way to do it. Just get me a large flag. And we'll just mark it with my logo or something. Or D. That's fine. Okay. So, we have our rotational data from the first offset. What I'm kind of like weird about is that the rotation on the rotation control on this is not exactly, it might not get us exactly what we want, which means we might have to have an offset, which that might make this a little bit complicated. Basically, if you look at side B of this triangle, this is a right triangle, this wing's a right triangle. If you look at side B, halfway through side B would be like right here, right? That's about halfway. Where we rotate it is not halfway. That might screw things up, but we'll see. You're a right triangle. I'm not. That is. Are you okay? All right, so now the next thing I'm going to do is make a piece for this to mount to, just so I have a master control for the sub-assembly. And I don't accidentally select the datum wing by accident. Accidentally select the datum wing by accident. Thanks, EJ. English is cool. All right, so this is going to be a piece of the wing, right? ATM machine. All right. Get rid of that, and now set my rotational length extension to that right there. Get them coplanar. They are exactly coplanar. I might configure this. Yeah. Let's see where this takes us. All right, so our entire offset here, let's see, what is the offset? Let's go to this one right here. What's that angle? We're starting at 2-degree offset, all right? So this should be able to make this compound curve. So set the angle controller. I see. That's why I set this to 360, so I could get the whole range of movement. I wish I could zero the damn thing, though. Alright, so now what we're going to need to do is what's 272 going to give me? We're going to need to start from the zeroed position. All right. Okay. All right. Datum extender. So we have 7 of these. Each one of them has a throw of 4.8. So I need to do some quick maths. 4.80 times 7 equals 33.6 meter extension. All right, cool. Cool. All right, now that's configured right. Datum extender needs to be set to 33.6. Rotational extender needs to be set to 33.6. There we go. Cool. All right, so I don't think so, Nova. Okay, so we have our first datum wing, right? And now we have to rotate that wing a smidge. So we need to set our master length extension to 1.9. The hell? Am I stupid? How many ticks is this? We're moving on 10 centimeter increments. So 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. 19 at a 10 centimeter increment tick is 1.9 meters. So wait, are we moving in 20 seconds? No. Don't tell me I didn't. We move in 20 centimeter increments. I thought it was 10. That's what I get for not playing for a little while. Yeah, so yeah, exactly. 3.8. Well, actually, I have to sync this to 0. Okay, we're synced to 0, so and that's the exact position. Let me just make sure. Why on earth is it 20 and not 10? I don't know unless I did some math wrong, which I'm kind of thinking that my math might be wrong. Are you going to use this automatically place each panel? Not so much that, but find the exact position where it needs to be. It's going to be hard with the offset being the rotational offset like that, but we'll see where it takes us. All right, so that's pretty much exact. Now we have to set this. I need to zero this in this position. That's kind of where we need to be. I need to zero it, and we need to go in the positive direction up to here. So let's take the cal. Let's zero it at 270. Well, what's the rotation here? Okay. Zero it at 90. And we have 90 degrees of rotation, so switch that back to 90. So that means that we zeroed this here like a dial indicator. So now all we should need to do is punch in 0.148 or 14285. Boom. It didn't take that to the decimal place. You see, with the tessellator before, we weren't working with decimal places. We were working with whole numbers. So I'm just trying to figure out a way to see if we can get this thing to go to the decimal. Maybe if I set this to 900. If we set that to 900, we could get to the decimal point, I think, a little bit better. Because something like that... No, that's still rounding to the 10th of a decimal point. Alright, so that means I need to plug the numbers in here. So, alright, just set that to 90. The decimal point here is what takes the number, I think. So... Got it. I got it. I know how to do this. Move the play speed down. All right. Actually, I really only need to do this to one of these. But that's fine. Oh, yeah. Score. Hey, Chaos, Spartship, what's going on? Offset the angle, origin. Yeah, Nulty, I'm trying... That's the big problem that I'm trying to work around right now. Trying to figure out how to do that. How do we offset that? But we'll get it in good time. Do you need a protractor? This is a protractor, dude. That's exactly what it is. So now... Okay.
Discovery, go at throttle up.
That's the rotational length extender. Which... The play position on the rotational length extender is set to 1.9. What the... What the balls, game? I set it to 1.9 and now it works. What the balls, man? What the frick? Why would you do that? I don't understand. It was 10 centimeter. It was 10 centimeter increments. I am going crazy over here, man. Hey, Just Face, what's up, dude? I am going a little nutty. All right, so that's where it needs to be. Now we just got to get our rotation. We got to get the rotation correct. But how are we going to do that? We need to go to the rotational, the angle controller here, and we need to set this to like 91, right? That's the difference. So this barely needs to move for now. Like, we'll zero it later. Also, I started my shoot this Friday on the EUS. I'll keep you all updated when you can. Nice. Cool, man. All right, what's our difference here? It's 2 to 1, so we have a 1 degree of difference, and that gives us 0.14285 gives us your diff offset over 7. Yeah, okay. Cool. So we need 1, 2, 3, 4, 5, 6, 7. Okay. Now, I don't know. Let's do 90 divided by 7 just to get it right. 12.8571. Copy. Time value 12.8571. So this next one is 25.71, 38.57, you don't necessarily need to do this. 51.42. Fucking stupid math. 64.28. $77.14. There. That's more or less right, the right spacing. Okay, so if we go to this point, right, at time 1286, now we type that value in. So this would be 90. So clear, dump the history, 90.14285. Or, well, let's try this, 90 plus 0.14285. Boom. Okay, so I should be able to copy this to the 5th decimal point as a value right in. And if I make it go to that point, right, we go back, we go to that point. Oh, that is a very, very subtle difference. But the rotation, yes, yes, we got it. Boop. Now plug this into right here. Paste that number right there. Boop. Copy that. Paste that number right there. Go here. Go here. $85.71. There we go. That's it. What's going on? You've been crazy since 7x7. I'm coming up with mechanical ways to implement wing tessellation. Or, well, basically a guide to do this right. Today, Junior! Alright. We got what we need. We should have our rotational increments. So go right there. And now we can eyeball it. Cool. All right, now if we get out of our angle controller and we go rotational length extender, this is what we want. Open this editor, right? .7. No. Yeah, that's right. That's the right extension. You got 9K. Why are you showing me that? Why are you showing me that? Hashtag pound sign, man. Okay, so now if I go to the angle controller, open up the editor, and we just boop. Actually, okay. I'm stupid. Please excuse the stupidity. I gotta build out the entire wing. Oh, why is this so hard? This came so easily to me before. Just move this over here. I'm gonna try something here. Let's see if it works. Burb. I'm going to try to see if we can incorporate an overlap. An overlap will get each wing's control node coplanar. They're coplanar on this the transverse axis here. So let's. It might work. Either that or I just made a lot more work for myself. But we'll find out. Okay, so I'm thinking. Okay, rotation is not going to work, right? Okay, cool. It's fine. All right, so we just moved this on 1.9. Yeah, turbo silencer. see what this does. See, this is gonna get me perfectly aligned. %, play speed. Good enough. Hello, Starlink still go for midnight? I think so, yeah. Wait a minute. Did I get that right? How is Plen? It's coming along, sweetheart. Yeah, I think we're going to the next one. I think we gotta go over here.
Discovery, go at throttle up.
There. Hey, Willard, what's up, dude? All right. Move that extender out there. Just get rid of the damn curve. Doesn't matter. All right, we can get rid of that. We know our increment, and I can line it up by sight. Okay. Save this. Get rid of that. Now let's take this shape, and it should exactly match those I-beams if we did this right. It should be exact. Like, exact to the decimal point. If I take this and we do that, hang on. Get a self-scope planer. Make sure that's right. Now all I should have to do is just take this thing and just do a slight rotation to it and try my best to get it basically perfect. Something isn't right. No, I took a gamble by offsetting these to try and get the rotational axis figured out like this. And it looks like the ones that we see. It would help if, you know, you actually space them how you want to space them, EJ. That would probably make a difference.
Discovery, go at throttle up.
Okay, well that's good news because that tells me that it's not the panel tessellator. It's not necessarily the panel tessellator, which is good. Alright, dump this. Get rid of it. Hey, Big Body, 68-month resub. Might be about time for a break. Nah, screw that adversity. I don't have time. I want to... Well, not I don't have time. Of course I have time. All right, start over. Start over. Start over. Not the entire thing. Not the entire thing. Just that particular sheet. That prototype did not come out right. That was a prototype. I didn't get this. I tried something new with the spacing, and I probably shouldn't have. That was bad for a test. So, take our rotational point, put it right there. Rotational point needs to be right there. Set it to the default position. Go here, rotational leg extender, move that back in, make sure our datum plate is perfectly aligned. Okay, angle controller, set that back to 0. We're aligned. Good. Okay. That needs to be right there. That's how those things fit together perfectly. But now our rotation on this is going to be slightly offset. I'm not sure how to solve that problem because we have an offset rotation on every child wing piece. But screw it. Might not be that big of a deal. Like maybe I just manually adjust it like what I did. All right, so now let's go here, take our time, make sure we do this right. Make sure our spacing is good. And I'm just going to make a test piece for this exact spot right there. Now, the other thing to kind of take into account is what the heck. Eyeballing this is going to suck, but that's whatever. It's all right. Okay, set this to that position right there. Make sure we're coplanar. Okay, bring up the angle controller, set it to that. The rotational length extender, 1.9. Okay, that's right. Now we take the piece that doesn't select the letter right there, rotate that into position. Okay, good. Next. Okay, cool. See, this will work a lot better when we don't have, it'll work a lot better when we have way bigger angles to see. That's right. Okay. Like, if we have to do more rotation than this, all right. Okay, last one. Okay. All right, let's see if it works. Did I make it backwards? Wait a minute. Yeah. Oh, I was touching left or right. Somebody said that in chat, and I was like, no, this is right. So I mirrored it. I did mirror symmetry, and then I pulled the right subassembly instead of the left and got a mirrored copy of it. Backwards, isn't it? It's freaking backwards. It's backwards, isn't it? It's backwards. It's backwards. Oh. Well, at least we know the tessellator is working. Reyes with a walk-off grand slam. Hey, that's good news. You gave me some good advice for my chopper, but in the end, my chopper was pretty good. I'm just a trash pilot. Oh, hey, Rocket. Sorry. I mean, that sucks. Hey, like I said, helicopters are hard. They're hard to fly, man. The more I learn about helicopters, the more I'm confused about how they work. Not confused, but the more I'm kind of, the more I'm fascinated with how they work, you know what I mean? But then again, right here, guys, our angles might be correct. We might just need to make adjustments. Yeah, something like that, right? Oh, well, there you go, Ryan. So where did we go wrong? Where did we go wrong here? Are we offsetting in the wrong direction? Hey Nazalik, I'm alright. Where did I go wrong? Do we need to offset in the negative? Right? Like, maybe... Because this looks right. It's just... Because see, it's gradually going up. But... Now I'm wondering if I did... Is that me? I don't know. if that's the case, if I flip this backwards and we align it that way, this should align perfectly. Let's just see if that does that. Are you unding stream soon? No. No, we're going for a little while, Junior.
Discovery, go at throttle up.
Getting it great. I'm trying to think where I went wrong here. Those angles are right. I know the angles are right. I know the offsets are right because we're lined up this way. And I know we rotated it on the right increments. So why are we so out of whack here? I rotated the right one, correct? Like, I know they're rotated. I thought I had it. I mean, that's right. I'm getting a little tired and I'm not exactly sure where I made a mistake. So, let's just try something here. Try it with a completely straight edge of wings, right? I did figure out the tessellator, but I'm not sure if the tessellator is going to be exactly useful here.
Discovery, go at throttle up.
Joe Dirte. Dirte is French. Joe Dirte game. Thanks for that game sub. Hopefully you get your Hemi, sir. Screw it. Banana. There needs to be some translation, I think. No, not translation. It's got to be rotation. No, it's got to be your bowl. Alright, start over. I can't believe I forgot how to tessellate wings. I'm a little embarrassed, but it's alright. Yep. Lyrics are applicable. No, not this part. All right, let's try a different build method. I'm trying to see if moving it on this axis. I think I may have gotten the axial rotation wrong, but we'll see. I think this might fix it. So now, what we got to do is take this and align it, and then we got to do it again. Align it. So switching that screwed with my offset rotation this way. So maybe rotate them first and then do this. That's no good. I'm sorry, guys. I'm coming. I'm drawing a blank. I apologize. I don't really want to go back to square one. It's just not, I'm just not getting it. It's not a root part issue, no. No, it's just the numerical combinations to doing the right type of wing tessellation. I forgot the workflow. This is an SSTO, yeah. I'm working on building the wings. When you build a wing this big, you can't... the shape of the wing and where the wings go absolutely matters. It makes a huge difference. It makes a huge difference. What if you pulled up that other craft file? The other big plane is already tessellated. You can see how you did it. Well, that's only going to show me how I put the parts together, Hired. It's only going to show me how I put this all together. It's not going to show me how I did it. You know? I know I made that plane manually, but yeah, I'm not... I think the panel tessellator really only works... I think the panel tessellator, the tessellator jig only really works when, with panels because they're equilateral. I don't know where they are, Bucket. I understand how the panel tessellator, what the panel tessellator is supposed to do, yeah, but... I'll just try one more shot at doing this manually, and we'll see if that gets us anywhere. There's something I'm really not taking into account here. And I'll be damned if I know what it is. It's getting a little late for me to figure this out. But this very much feels like one of those things that... It feels like one of those things that you, like that you need to sleep on. You know what I mean? But whatever. Hey, we're going to the launch, so I mean it's not gonna hurt taking a stab at it. You know what I mean? Let's try. So I did the rotation upwards first, and now let's take the next one and see if we can get that aligned. That's good. Okay, so now do the rotation this way, right? That one seems to be okay. It's pretty dang parallel now, so take this one, get that more or less aligned. Now how do we look here? Now do the rotation. That one needs to go down just a smidge. Like that. And now, see if we can rotate it to where we need it to be. Yeah. Okay. Set that up like that. Now rotate it this way. Now it needs to go a little bit more. Okay, so now all that's left to do is rotate these so the seam matches. You just gotta these ones are going to be very subtle. They're going to be hard to see because it's a very, very short angle, especially when we're close to this. Okay, not bad. Can't wait to see this thing fly. Take as much time as you want. Yeah. I'll get it. Dude, I am persistently, I'm stubbornly persistent. I will just begrudgingly keep going. I believe in pushing yourself, and I'm really trying to do that. Trying to do it here as best as I can. Give me the music. Lowrider. Lowrider, Downey. Downey. Lowrider. Here. Let's go over here.
Shorty had them apple bottom jeans. Boots with their fur, whole club looked at her. Baggy sweater pants and Reeboks with the straps gave that big booty a smack.
It's classic.
$1 million vibe bottle to go. Their birthday cakes, they stole the show. Next thing you know, Shorty got lost. Shorty got lost. Shorty got lost. She got up, Shorty got up.
I needed that. Pavarotti, yeah, of course. Is there a Boots with the Fur version of that? What? Just listen to it. Thunderhead 289 opening? Yeah, no, man, that's weird. freehanding it. Screw it. Is there a SpaceX launch in Vandenberg today? Yes. That's it. Oh. I got it. I know how to do this. I think I got it. Can you link? You have the link? Sure. This song is friggin' sweet. I got it. I got it. I know what we need to do. So honestly, I need to do this one more time. We need to go here, like that, and then set the angle like this. It's this. We're rotating on the wrong axis. I got it. This one's the ones that the wings that are pointing that way. We rotate on this axis, right here, that one, and then these ones should. Yeah. Okay. All right. I think I got it. That goes there. But if that was the case, how then this piece right here is not going to be right. It's Allison. That band sounds like Alice in Chains, dude. Yeah, that's why I like Scorn. Scorn's awesome.
Discovery, go at
Platinum, hey, what's up, dude? 87 months. think I got it. Let's see. I gotta be careful about song suggestions, Ultimate. I have to clear stuff for DMCA. I don't need to go have fun with that. Sorry, man. It seems like we might need to do rotation on both sides. Okay. All right. I'm just gonna have to brute force my way back into learning this, dudes. Sorry, I know it kind of sucks. But we got some good tunes. We got to launch soon, so let's just roll. Yeah, dude. Joe, the singer for this band sounds really close to Lane. It's kind of ridiculous. But yeah, good band, dude. That's ridiculous, dude. Are you curbled yet? No. All right. I'm telling you, man, once I get this to click, once I figure it out in my head, how this thing goes back together, we got it. There. And whereabouts do we want the wing to be completely flat? Let's go right here. I'll use that as kind of a marker. What happens if we do this? Joe's been busy. Dude, have you seen what Joe's up to? It's unbelievable. Guy's a beast, man. Guy's an animal, man. All right, this is the workflow. So I have these wings put together slightly different. Instead of the inverse wing being attached to the next one, it's attached to the first one. This forces a different workflow. Watch. So set that. All right, cool. Now, set this like this, right? This is where I was getting confused, because you need this one to set the angle. You need to move these wings, the ones that are facing towards the front of the plane, they need to be moved on the green axis. And these ones need to be moved on the red. I got it. 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 Holy balls, it only took me freaking 10 hours and 40 minutes. I got it. That's how we do it. Oh, thank God. Oh, my goodness. Watch. That's how I did it. I literally just brute forced that back into my head. That's the best way to describe it, man. Brute force that thing back into my head. Oh God. It's the control piece. You have to control these ones on one axis and that one on the other axis, but I've been making them wrong. This one needs to be attached to that one. That one needs to be attached to this one. I've been attaching one to one to one to one to one. That's wrong. That's not how you do it. No, Ryan, that's wrong. Don't turn that damn wheel. Watch. So, if we do this, right? Flip this around. Flip it over. Let me just look at that. All right, that's fine. Perfect. Now, I've been attaching this piece for the next one. I've been attaching to this one. You attach it to that one. All right, watch. Ready? This is the hierarchical setup. That's how you do it right there. Okay. That's one row. That's our straight row. That's the control. Hit the save button. Watch this. So the next one, right? You got to go here like this. Move this into position. Do the overlap. Now we got to move this backwards. Okay. Save. Now, this one we move on the blue axis. Okay? Actually, on local it'd be green because that's the local offset for the part, right? Move this into position. Line it up. Take the back control node, this one. Rotate that one on the red axis. Now, align it on the green. And then just rinse and repeat, baby. Wait a minute, hold up. We didn't line up there. Why didn't we line up? How's KSP 2 coming along? They making progress? 3 for the day. Yeah, Hawker. Next patch should be coming out soon. You guys want that song? I got you.
Well, this is unbecoming. Social
Got your back, dude. How'd the truck turn out, J-Nick? Pretty good, dude. Oh, dude. Oh, yeah, dude. I've been driving her around all summer. Gotta wash the thing. I've been driving it so much, I freaking gotta wash it. Yeah, man. She came out awesome. I think. Oh no! I misclicked. Come on, game. Kerbal's fighting me tooth and nail today, dudes. Control Z will break all my hollow fairings is the end of that sentence. How is it on gas? Could be better. Maybe I have the axis controls backwards. I know you have to use different axes here, right? So there. Okay. Still saving to fix my car. I wish I had a garage to do it myself. Yours looks awesome. Thanks, Nagwall. I mean, it's not the worst MPG, guys. But hey, whatever. I mean... I'm still honing in on how I did this. I'm getting closer to the workflow, but I had this down to a T at one point. You have to adjust certain axes first. I think I got it, but I'm thinking if there might be a better way to do this. But no, there's a reason why I did this way. Okay. All right, I think I got it. Okay, so let's aim. Right there. I'm not second guessing. I'm just not finding the right way to do this, man. Alright. Let me look at the K90. Let me see how I attach those. Maybe that'll give me a clue. I thought I had it, but... Yep, this one controls the next one. Yep, okay. I did do it that way. I did have that right. It wasn't 1, 2, 3, 4. Cool. Keen, they're not on Spotify or anything, dude. They sound like AIC, Keen. Yeah, for sure. Here, I'll link you the song. Good tunes, right? It is good stuff, dude. You have to freehand it. Okay. Gotta freehand it. I see it. I see what I have to do. Okay. You have to freehand it. This, just the way this is set up is going to be really difficult to get this right with panel tessellation, like via a jig, like what we did previously with the shuttle. It's going to be hard to get that right. So, what we need to do. Oh, okay. Okay, that's the way I'm doing this. All right. Colin, the playlist thing gonna work. That's not the playlist I'm listening to. Who knows the last time that playlist command had worked? To be honest with you, just ask me if you like the song, and I'll link it to you, dude. I'm old school like that. I don't know why I would have chosen to do this a different way with the K90, but this is just me basically giving myself a crash course into what I did previously. I think this is the one that we're gonna go with. This is the original thing, the original way I put the wings together this afternoon, probably about 8 or 9 hours ago. But with a little bit of a different workflow. So here, let's do this. Here, we'll change the tunage up a little bit. This is good working music. Yeah, this is test shot. Yep. All right, so that one. And then we'd set that one, but that one's fine. Now that one needs to go into place. Like that. Okay, cool. Now set this guy. Because our rotational nodes are offset between the two triangles, we're going to need to do some translation to get this right, like that. Because there's a translate offset, that's why this thing didn't work. That's why the tessellator didn't work. It didn't do what I wanted. Now we take the child node right here. Set it to the same rotation. Translate it.
Listen, Tranquility Base here. The Eagle has landed.
Hey, Anon, thanks for the tip. I appreciate it. You're staying live till the launch. That's the plan. Really wish SpaceX would stop freaking launching stuff at midnight. El Sai Congru. Sure. The new astronauts, Nova. am starting to get tired, though. What hours of wing tessellation will do to your brain. Yep.
Discovery, go at throttle up.
Orange, 50-month resub. Thank you. Okay. Let's try this again. I think I've gotten to the point where I'm thinking about this too much, dudes, but I'll keep going just because we're going to the launch. I think if it was any other night, I probably would have stopped. Hopefully, sometimes when I sit here and brute force it though, like I try to figure it out,
Discovery, go at throttle up.
for whatever reason, if I sleep on it, the solution becomes very apparent the next day. So maybe we'll come back tomorrow and I'll be like, yep, that's what I was going wrong. I think what's screwing with me right now is that I'm trying to think about this like panel tessellation, and you can't, because if you look where the node is to rotate this piece and you look where the node is to rotate this piece, they're not lined up. And that is really, really messing with my brain. And what I've been trying to do here is I'm trying to figure out exactly how I did the panel tessellation with wings, or the wing tessellation, because I thought it was just a modification of panel tessellation, and it's not. It's not. Thinking about it, I haven't done wing tessellation on anything since the K90. We finished the K90 in 2020, by the way. Yeah, that thing's 3 years old, but yeah, just thought I'd let you know. But we should be a little ways out from the Back X launch. There we go. is why we can't build F1 engines anymore. The know-how is lost to time. Yeah. There. Well, all right. Okay. Now it's this one right here. We got to rotate this a little ways. A little bit of translation action. Now rotate it on the second axis this way to get it to line up. Like that. And now take this individually and then line that up to the I-beam again. Translate it down a little bit, translate it over for second axis right there. And now over here, use this axis to line us up again. Like that. Took me frickin' long enough. I think I got it though. think I got it. I don't know how many times I've actually said that tonight, but whatever. All right, let's inspect that first seam. There's a little bit of a crease right there, but that's okay. This reminds you of a Rubik's Cube? Yeah, Curtis, I know, right? That's following that contour pretty well. For the first time in a little while, let's move on to the second one. So, rotate, local orientation, snap off. Rotate up first. Like that. Then rotate this piece into position. Actually, I don't think we might not even need to do the translation stuff. We might be able to handle it with rotation like this. This. And then switch that rotation. Okay. Man, this hurts my eyes. Okay. Like that. Oh, yeah. Nice. Nice. Very good. Might take a little more time for me to hone in that workflow, but... Okay, I think we're getting there. I just kind of feel bad, all that freaking math that I did out about spacing and stuff. I mean, but then again, it wasn't for naught because I still have the guides, but it still sucks. That we couldn't get a tessellator solution. I mean, I can sculpt it by hand. It's not too bad, but it could be better. It's starting to look real sharp. Thanks, dudes. Sorry, I totally forgot how to do this, and I basically brute forced it back into my brain. Like, just by sitting here and trying stuff until I figured it out again. Like, basically, it's given information to know that there is a way to do this. I just don't know what that given way is. Should start a video series called EJ Tutorials for future EJ. Yep. Yeah. So, right now, guys, I'm kind of only working on the area that we have defined right here, just to make sure this works. I started to work out here, but I said, yeah, whatever. We gotta figure out the right definitions for out here. But yeah, the I-beam guides are still working pretty well. We just needed to remember how to put the stupid thing together. Okay, this piece. Two more, and then we'll take a look at the whole thing again. Okay, one left. I don't know if you guys knew it's 85 again. All right, let's take a look. There's your payout. That's why I wanted to make sure we got this right. Look at that. Oh, yeah. There's some seamage going on right there, but... we can tighten it up. There's still some more right there that we can tighten up. So the whole thing about wing tessellation is that if you get it right, you look at it from the top and it looks flat. But if you look at it from this way, it does not look flat. It's a concave surface. That's why I took my time to get this right. I think we're on the right track with the workflow here. Yeah. See what I mean? It looks like there's still some seamage here. But that's not something we can't fix. Awesome work. Thanks, guys. Thank you. Thank you, thank you, thank you. Yeah, see, there's some seamage right there, some seamage right there, but for the most part, that's good. Not bad for using our hands, huh? We can iron these kinks out by just doing this, and then a little bit of this. That's so freaking hard to do. My hands freaking hurt. My hand hurts from freaking the steady hand that you need to do it. But damn, dude, look at what we got. Oh yeah, baby. The death precision grip, indeed. Yep. Now we're cooking with methane. We're good. I got it. Oh, dude, look at the back of this thing, man. Oh. Yeah, ignore the seams out here. That's not finished yet. What engine are those? Mammoth engine? Or Mastodons. And this should be pretty dang strong. If everything is grandparent strutted bucket, and then I need stringers on the long axis to strut them together. Yeah, it'll be strong. The engine's gone. I took them out while I was working on the wings. If you want, fellas, I'll put them back in. The Schrubber engine. Thanks, Joe. I appreciate it. Hey, thanks for that sub today, man. Yeah, the Schrubber engines are... Yeah, I started moving around the mounts. What is the Schrubber engine? That is the Star Raker atmospheric breathing engine component, or Schrabeck for short. We call it the Schrubber engine. It's a turbofan ramjet. Yeah, bypass turbofan ramjet. Kind of like an SR-71 motor, but kind of not. We need 10 of them. Yeah. Oh, it's a pre-cooled too. Pre-cooled bypass turbofan ramjet thing. Yeah, it has a logarithmic casing of prefamulated amulite. That's right. That's correct. Don't forget the spurving bearings. It has 2 spurving bearings in direct line with a panometric fan. What will you use for ohms? Terrier engine should be fine. I ripped the engine mounts off by accident. It's okay, I don't think we're not going to lose anything because I hit the save button. How much RAM is Kerbal using? Okay. Okay. Yes, it's using all the RAM. About that much. KSP. I am the RAM. Oh my goodness. That's freaking sweet, dude. That shape is mint. I'm really, really happy with that. That's freaking cool. Guts, glory, ram. Like I said, you know your wings are tessellated right if you look at it from the top and it just looks like a straight grid. If you see anything like this, any imperfections like there and there, you just have to adjust the rotation a little bit. But other than that, you are goody goody gumdrops, man. We had a slight seam right there. What's it from? Not getting the rotation exactly right. Screwed up the seamage just a little bit here. It was probably because I couldn't see the control. Couldn't see the controls correctly because the I-beams were in the way. The I-beam guides that I made. We gotta find a better way to make guides, dudes. That's something I gotta work on. It's impressive how far along you are on this design. Thanks, man. Yeah, see, now we can just fine-tune. And I swear all the other tessellated surfaces on this are not going to take nearly as long because I know how to do it now. I remembered. At least I think we got it. I'm not 100% confident that this is the exact way to do it, but I think it's on the right track. And once again, we got a couple of seams here and there, but the antenna is almost that length. Yeah. I'm thinking strut rulers might be a good way to do it. Either way. The more and more I'm messing with this, the more and more I don't think I need to really mess with the translation node, but I think we still need to just like maybe a smidge. No. No, no. Up. Yeah, see? Yeah, alright. That's pretty smooth, man. I wish you could export and import these in Maya in Blender. Yeah, that would be super useful. Your boy knows how to use Maya. I'm pretty damn good with it, actually. That would be very useful for me, man. Absolutely. Starlink is starting soon. Yeah, alright. We capped the day off with a sweet Starlink launch. Yeah, see, some of these are a little out of whack because we free-handed it, but we can fix the seams. I'll fix the seams with a clear head tomorrow. I'll probably just delete this and make it again, but there you go. Can you attach two small parts together and then offset one of them and then strut them to have a ruler of any desired length? I do that with cubic octags, Nick, to create profile curves. I usually use the profile curves to make fairings. That's actually how I got this shape to conform around the shuttle cockpit nicely. Here, take a look. Ready? What do you think now? See what I mean? I can do that with our wing shapes. And yeah, you can create a strut, and the strut is not collidable, so you don't have to worry about like it being in the way. Yeah, I also did it with the back fairing. See? I use fairings to make curves. And those profile curves, if we could do them with wings, that would actually make it pretty easy. Can you imagine if we did them this way with the wings and did that way as well? And basically made a grid of every intersection point where all the wings come together. So 1, 2, 3, 4, 5, and 6. We did that. If we did that, we'd be pretty good. Anyway, I'll leave that here. We'll take a look at it tomorrow. But that does look right. It looks correct. We gotta work. We have to just hone in on this, work on this. I'll probably give it another shot tomorrow, but I got it. I'm pretty sure I figured it out. Anyway, let's cap off the stream with a Starlink, shall we? You guys in? I hit save, don't worry. Time to free up some RAM and let my PC breathe again. Just a quick goggling. Is anyone using Maya for KSP mods and models? I could make the models. I think what J-Nick is, or not J-Nick, I think what was said, Weather Guy, is like if I could export the parts and then place them with the channel box in Maya, like if I had decimals, if I could see the decimal rotation of each part locally, I wouldn't need like an I-beam with the robotic piece to set it. I could just set it in the channel box, and I could probably make that shape in about 5 minutes in Maya. Yeah, very easy. Very easy. With control curves and whatnot, super easy to make. But because I have to control each individual wing, and you kind of have to do it by sight, you know, it doesn't really... I can't be precise. The robotics and the tessellator is the way to be precise, but yeah, that doesn't really work when you have the offset nodes with the wings. One of the things I really asked for KSP1 that they're probably never going to add was a channel box, something that shows the local degrees rotation and the local translation or absolute translation of parts relative to their parent. That would be really, really useful. I could do... If it was like Maya and we had the channel box with rotation info, I could build whatever you want. I mean, I can get pretty close right now, but we could build anything. Anything, any shape, doesn't matter. Just give me the right wing parts and I'll be able to put it together. Gotcha. I'm afraid when it comes to Maya, at least, I'm grasping at straws. I figure I'd give it a shot. You're afraid when it comes to Maya? What's wrong with Maya? Oh, for Pete's sake. Why you no work? What mission is it? Where's next space flight? I'm gonna mark it for drummer. 6:20.